The darkness stretches beyond our vision, beyond our understanding, beyond even our imagination. When we look up at the night sky, we're not just seeing stars and planets. We're staring into an abyss so vast that the human mind cannot truly comprehend it. This is the universe in all its terrifying glory, a place where the laws of physics as we understand them break down, where time itself can bend and twist, and where forces beyond our comprehension shape the very fabric of reality. The universe is horrifying precisely because it is unknown. Our species has evolved on a small, wet planet, circling an unremarkable star in a quiet corner of an average galaxy. Our entire evolutionary history has prepared us to fear predators, to worry about the dark cave where something might be hiding, to be concerned about immediate threats to our survival. Nothing in our development has equipped us to emotionally process the sheer scale and alienness of the cosmos. Consider this. Light, traveling at nearly 300,000 kilometers per second, takes over 4 years to reach us from the nearest star outside our solar system. Our galaxy is so enormous that light requires 100,000 years to cross from one side to the other. And beyond our galaxy lies billions more, stretching out in all directions for billions of light years. In this incomprehensible vastness, anything could be lurking, cosmic horrors beyond our wildest nightmares. But it's not just the vastness that terrifies us. It's also the understanding that the universe operates according to rules that seem to defy our common sense. Quantum mechanics tells us that particles can exist in multiple places simultaneously until observed. Einstein's relativity reveals that time itself is not constant, but can stretch and compress depending on gravity and velocity. Black holes contain singularities, where our mathematics breaks down entirely. These are not just curious scientific facts. They're fundamental challenges to how we perceive reality. Our brains evolved to navigate the African savanna, not to contemplate quantum superposition or the expansion of space-time. P. Lovecraft describes the terror that comes from confronting realities so alien to human experience that they break our minds. Lovecraft's fictional monsters were horrifying not because they might eat us, but because their very existence suggested that the universe was fundamentally different from what we thought, indifferent to human concerns, operating according to laws we could never fully comprehend. Modern astronomy and cosmology have revealed a universe that is, in many ways, more bizarre and unsettling than anything fiction could invent. We live in a cosmos where stars can collapse into objects so dense that nothing, not even light, can escape their gravitational pull. We exist in a reality where time began in a singularity we call the Big Bang, and where the fate of everything might be endless expansion into cold, dark nothingness. What then counts as horrifying in space? It's not just the phenomena that could physically destroy us, though those certainly exist. Rogue planets hurtling through the darkness, gamma-ray bursts that could sterilize entire regions of a galaxy, or the eventual death of our sun. The true horror lies in the cosmic indifference, the sense that the universe was not made for us and operates without concern for our existence. Humanity could disappear tomorrow, and the cosmos would continue its inexorable expansion. Stars would continue to form and die. Galaxies would continue to collide, all without anyone to witness or remember us. Another source of cosmic dread comes from the possibility that we are not alone. For centuries, humans have wondered if other intelligent life exists among the stars. Recent discoveries of thousands of exoplanets have made it seem increasingly likely that Earth is not unique in harboring life. But this raises unsettling questions. If intelligent life is common, why haven't we detected it? Are we truly alone, or is there some reason advanced civilizations remain silent? Could there be predatory species out there, waiting in the darkness between stars? The silence of the cosmos might be more terrifying than any signal we could receive. Even our place in time is unsettling when viewed from a cosmic perspective. 8 billion-year history of the universe. We are latecomers to a stage that has seen the birth and death of countless stars, the formation and collision of galaxies, the slow evolution of cosmic structure. And the universe will continue long after our species, our planet, even our galaxy has disappeared. We are ephemeral beings in an eternal cosmos. The horror also comes from the limits of our perception. Our senses evolved to detect a narrow band of electromagnetic radiation we call visible light, to hear sound waves within a specific frequency range, to feel objects at a human scale. But the universe contains phenomena that operate at scales and through forces we cannot directly perceive. Dark matter, which makes up about 27% of the universe, doesn't interact with light or any electromagnetic force. We can detect it only through its gravitational effects. What else might exist beyond our perceptual abilities? What realities might intersect with ours without our knowledge? As we journey through the darkest secrets of the cosmos in the pages that follow, we will encounter phenomena that challenge not just our safety, but our very understanding of existence. From the vast emptiness of cosmic voids to the violent deaths of stars, from wandering planets doomed to eternal night to signals from the deep universe that might indicate we are not alone, each revelation forces us to confront our place in a universe that is stranger and more terrifying than our ancestors could have imagined. The exploration of these cosmic horrors is not meant merely to frighten, but to inspire a sense of cosmic perspective. There is a peculiar awe that comes from confronting the unknown, a sublime terror that reminds us of our fragility and our remarkable good fortune to exist at all. In the face of such overwhelming cosmic indifference, human connections and the brief flicker of consciousness we experience become all the more precious. So as we turn our gaze outward to the greatest darkness and the most extreme conditions the universe has to offer, remember that the ability to comprehend these horrors, to name them and study them, represents one of humanity's greatest achievements. We are the cosmos becoming aware of itself, even the parts of itself that terrify us. Our journey begins with one of the most fundamental horrors of the cosmos: emptiness. While we tend to think of space as merely the distance between objects, there are regions of the universe where the emptiness itself becomes a character. Vast, ancient voids where the usual rules of cosmic structure seem not to apply. These cosmic voids represent not just the absence of stars and galaxies, but mysteries that challenge our understanding of how the universe evolved. In the darkness between galaxies, in the silent expanses where stars fear to form, we find our first cosmic horror, the void itself. And as we will discover, sometimes nothingness can be the most terrifying thing of all. The human mind has long been fascinated by astronomical phenomena. Ancient civilizations mapped the stars, tracking their movements and creating elaborate mythologies to explain celestial events. They saw patterns in the chaos, constellations representing heroes, animals, and gods. This was humanity's first attempt to impose meaning on the incomprehensible vastness above. But as our telescopes grew more powerful and our mathematics more sophisticated, we began to glimpse the true nature of the cosmos, and it was far stranger than our ancestors could have imagined. Consider the night sky from Earth. To the naked eye, it appears filled with countless stars, suggesting a universe teeming with light and matter. But this is an illusion created by our limited perspective. The spaces between those pinpoints of light represent distances so vast that entire civilizations could rise and fall in the time it takes light to cross them. And beyond what we can see with our most powerful instruments lies more darkness, more emptiness, stretching perhaps to infinity. This is the paradox of cosmic horror. The universe is simultaneously too big to comprehend and yet terrifyingly empty. The late astronomer Carl Sagan once noted that we are made of star stuff, that the elements in our bodies were forged in the nuclear furnaces of ancient stars. But he also acknowledged the profound isolation of our position. The cosmos is within us. We are made of star stuff. In this poetic observation lies a terrible truth. We may be the only conscious entities in our corner of the universe capable of contemplating these horrors. As we embark on this exploration of cosmic terror, remember that these are not just abstract scientific concepts. They are the reality in which we exist, the true nature of our home in the universe. The floor beneath your feet, seemingly solid and dependable, is actually part of a small rocky planet hurtling through space at 30 kilometers per second around a nuclear fireball we call the Sun. That Sun, in turn, orbits the center of the Milky Way galaxy at about 220 kilometers per second, and our entire galaxy moves through intergalactic space at 600 kilometers per second. We are never still. We are never safe. We are travelers on a cosmic journey we neither chose nor can escape. As we peer deeper into the abyss, prepare yourself for revelations that will challenge your sense of security and place in the universe. From the mind-bending physics of quantum mechanics to the earth-shattering power of supernovae, from the silent threat of invisible black holes to the mysterious signals emanating from distant corners of the cosmos, each revelation brings with it a new perspective on the true nature of reality. The universe doesn't care about us, it doesn't even know we exist. And in that cosmic indifference lies perhaps the greatest horror of all. The realization that all our struggles, our achievements, our very existence may be nothing more than a fleeting coincidence in an uncaring void. Yet paradoxically, this same realization can inspire a profound appreciation for the brief moment of consciousness we experience, a gratitude for the unlikely series of events that led to our existence, and a determination to understand as much as we can about the magnificent, terrifying cosmos we inhabit. The psychological impact of confronting these cosmic realities cannot be understated. Throughout human history, our species has developed various mechanisms to shield ourselves from the terror of cosmic insignificance. Religion often places humans at the center of creation, the special focus of divine attention. Science, while revealing the true scale of the universe, also empowers us with knowledge and the illusion of control. Art and literature create meaning through narrative and metaphor, but in quiet moments, when we stare into the night sky and truly comprehend what we're seeing, the protective barriers fall away, and we confront the abyss. Philosophers have grappled with this existential dread for centuries. These thinkers understood that confronting the true nature of the cosmos means confronting profound questions about our existence, purpose, and ultimate fate. Modern psychology recognizes a phenomenon called the overview effect, a cognitive shift reported by astronauts who have seen Earth from space. Looking back at our pale blue dot suspended in blackness, they experience a sudden, overwhelming awareness of both the fragility of our planet and the arbitrary nature of national boundaries. Many report a profound sense of connection to humanity as a whole and a newfound perspective on our place in the cosmos. This is cosmic horror transformed into cosmic awareness, the terror of insignificance balanced by the wonder of existence. But for every astronaut who has experienced this transformative perspective, billions of humans remain earthbound, experiencing the universe primarily through the images and data collected by our telescopes and space probes. These technological extensions of our senses have revealed wonders beyond imagination and horrors beyond comprehension. Consider the images from the Hubble Space Telescope's Deep Field Survey, which pointed at an apparently empty patch of sky for 10 consecutive days. The resulting image revealed not emptiness, but thousands of galaxies at various stages of evolution, some so distant that their light began its journey toward us when the universe was young. Each of those galaxies contains billions of stars, and recent discoveries suggest that planets orbit most stars. The sheer number of potential worlds is staggering and raises the unsettling question of why, in such a crowded universe, we have detected no signs of other intelligent life. Or ponder the images from NASA's Parker Solar Probe, which has ventured closer to our Sun than any previous human-made object. These close-up views of our nearest star reveal a violent, churning surface of plasma, heated to millions of degrees, with magnetic forces twisting and snapping in massive eruptions that could engulf Earth many times over. Our very existence depends on this cosmic furnace maintaining its delicate balance of nuclear fusion, a process that will eventually fail as the Sun exhausts its hydrogen fuel in about 5 billion years. The James Webb Space Telescope, with its unprecedented ability to peer into infrared wavelengths, is now revealing the earliest galaxies formed after the Big Bang, showing us the universe as it was in its infancy. These observations confirm what theoretical physics has long suggested. The universe has a history, a biography from birth to eventual death. And like all biographies, its story will have an ending. This cosmic narrative forces us to confront not just our physical insignificance, but our temporal insignificance as well. The average human lifespan is less than 1/billionth of the current age of the universe. 8 billion year history of the cosmos were compressed into a single Earth year. Human civilization would occupy only the last few seconds of December 31st. We are, in cosmic terms, the newest of newcomers, and yet, paradoxically, we may also be among the earliest intelligent observers in our galaxy. Studies of stellar evolution suggest that terrestrial planets capable of supporting complex life have become increasingly common as the universe has aged and become enriched with heavier elements. If intelligence is indeed rare, we might be among the first species in our cosmic neighborhood to evolve the capacity to contemplate the universe. This possibility carries its own existential weight. Are we the universe's first attempt at self-awareness in our region of the cosmos? The concept of scale lies at the heart of cosmic horror. Our brains evolved to operate at the scale of immediate survival concerns, predators, food sources, tribal conflicts. We can intuitively understand threats and opportunities that present themselves at the scale of human bodies over timeframes of seconds, minutes, or days. But cosmic phenomena operate at scales so far removed from human experience that we can comprehend them only abstractly through mathematics and computer models. Consider a supernova, the explosive death of a massive star. In a matter of seconds, a dying star can release more energy than our sun will produce in its entire 10 billion-year lifetime. The shockwave expands at thousands of kilometers per second, potentially sterilizing any planets within several light-years. The concept is simple enough to state, but the true scale of such an event defies visceral understanding. We can calculate the energy released, simulate the process on computers, even observe distant supernovae through our telescopes. But we cannot truly feel the scale of such cosmic violence in our bones the way our ancestors felt the threat of an approaching predator or the promise of a gathering storm. This disconnection between intellectual understanding and emotional comprehension contributes to the unique character of cosmic horror. We know, intellectually, that a gamma ray burst from a distant star could potentially sterilize Earth without warning. We understand mathematically that the expansion of the universe will eventually lead to the heat death of everything we know. We comprehend, theoretically, that quantum fluctuations may have spawned countless other universes with different physical laws. But these facts remain abstract, unable to trigger the immediate fear response that evolved to protect us from more immediate dangers. And perhaps this is a mercy. If we were to feel, with the full emotional weight of our evolutionary fear response, the true scale of cosmic dangers and our absolute helplessness in the face of them, we might be paralyzed with terror. Instead, we remain curiously detached, able to study and even appreciate the beauty in these cosmic horrors from a safe emotional distance. Yet there are moments when the veil drops, when looking at the night sky on a clear night far from city lights, or contemplating the age of the ancient light reaching us from distant galaxies, or considering the inevitable death of our sun, when the true scale of cosmic reality breaks through our psychological defenses. In these moments, we experience what the philosopher Edmund Burke called the sublime, a mixture of awe, terror, and wonder that overwhelms rational thought. This sublimity lies at the heart of why we're drawn to cosmic horror even as it terrifies us. There is something profoundly human in the desire to comprehend that which exceeds our comprehension, to name that which defies description, to find meaning in a universe that offers none. As we explore the darkest corners of the cosmos in the pages that follow, we are engaging in an act of defiance against our own insignificance, asserting our right to know, to understand, even if that knowledge brings neither comfort nor power. But perhaps the corollary is equally true. Somewhere, something terrifying is waiting to be discovered. And in our journey through the most horrifying aspects of the cosmos, we will find that the incredible and the terrifying are often the same phenomena viewed through different lenses of human perception. As we prepare to venture into the cosmic void in our next exploration, remember that the darkness we're about to encounter isn't just physical, it's conceptual. The vast emptiness between galaxies represents not just an absence of matter, but a challenge to our understanding of how the universe formed and evolved. In these great cosmic deserts, larger than millions of galaxies combined, we find puzzles that continue to confound our best theories and observations. And so we turn our gaze outward, beyond the comforting light of nearby stars, beyond the familiar structure of our home galaxy, into the greatest darkness the universe has to offer. What waits for us there isn't just empty space, it's a reflection of the limits of human understanding and the boundless mystery of existence itself. We often think of space as a canvas dotted with celestial bodies. Stars burning bright against the darkness, planets tracing their orbits, galaxies spiraling in cosmic dance. But this comforting image obscures a more unsettling truth. Most of the universe is empty, not just empty in the way we might imagine a vacant room, but profoundly, incomprehensibly vacant, devoid of matter, energy, even the quantum fluctuations that characterize what physicists call the vacuum. These are the cosmic voids, and they constitute some of the most terrifying regions in our universe. Imagine darkness so complete, so vast that it swallows entire galaxy clusters. Picture emptiness extending for hundreds of millions of light years in every direction. These are not mere gaps between stars, or even the spaces between galaxies. These are cosmic structures so large they defy our understanding of how the universe should be organized. And among these great emptinesses, none is more infamous than the Bootes void. Discovered in 1981 by astronomer Robert Kirshner and his team during a survey of distant galaxies, the Bootes void represents a volume of space approximately 330 million light-years in diameter that contains almost nothing. To put this scale in perspective, our Milky Way galaxy is roughly 100,000 light-years across, meaning you could fit over 3,000 Milky Ways end-to-end across this single void. The emptiness is not absolute. Scattered throughout this enormous volume are perhaps 60 galaxies, when we would expect to find thousands, based on the average distribution of matter in the universe. The very existence of the Bootes void, sometimes called the Great Nothing by astronomers, raises disturbing questions about the nature of cosmic structure. How could such an enormous region of emptiness form? What forces could sweep clean a volume of space larger than millions of galaxies combined? Our current models of cosmic evolution suggest that smaller voids can form naturally as gravity draws matter into filaments and walls, leaving behind regions of relative emptiness. But the sheer scale of the Bootes void stretches these explanations to their limits. Some astronomers have proposed more unsettling possibilities. Perhaps the void represents the aftermath of some inconceivably powerful event that cleared away matter on a scale we can barely comprehend. Others have suggested, half-jokingly, yet with a shiver of genuine unease, that it could be the result of intelligent intervention, a cosmic engineering project by a civilization so advanced that they can rearrange galaxies like chess pieces on a board. While mainstream science rightfully dismisses such speculation, the very fact that serious astronomers occasionally entertain these thoughts speaks to how anomalous these structures appear. What would it be like to be inside such a void? Imagine a civilization evolving on a planet orbiting a star in one of the few galaxies scattered within the Bootes void. Their night sky would be almost entirely dark, with perhaps a handful of distant smudges representing neighboring galaxies. They would have no concept of the rich tapestry of cosmic structure that we observe, the beautiful clusters, the delicate filaments connecting galaxy superclusters, the complex dance of gravitational interaction that shapes our visible universe. They might develop a cosmology that views the universe as fundamentally empty, with their galaxy as a rare exception to the rule of nothingness. How would such a perspective shape their philosophy, their religion, their understanding of their place in the cosmos? Perhaps even more disturbing is the thought that we might be moving towards such emptiness. Observations of galaxy movements reveal another cosmic mystery, known as dark flow, a pattern where thousands of galaxy clusters appear to be moving in the same direction at incredible speeds, as if being pulled by some enormous gravitational attractor beyond the observable universe. First reported in 2008 by a team analyzing data from NASA's Wilkinson Microwave Anisotropy probe, dark flow suggests the existence of structures so massive they can influence the movement of galaxy clusters across billions of light years. While subsequent observations have called the dark flow phenomenon into question, the possibility remains that our cosmic neighborhood might be responding to gravitational forces we cannot directly observe, perhaps massive structures beyond our cosmic horizon, or even the gravitational pull of other universes in a multiverse scenario. If such forces are indeed at work, they could eventually draw us toward greater cosmic emptiness, as the accelerating expansion of the universe simultaneously drives other galaxies beyond our observable horizon. The horror of cosmic voids extends beyond their mere emptiness. These vast regions also challenge our fundamental understanding of physics. According to our current models, the universe began in a state of incredible density and homogeneity. The Big Bang should have produced matter distributed relatively evenly throughout space. Yet structures like the Boots void indicate significant deviations from uniformity on scales that are difficult to explain. These anomalies have led some cosmologists to question our models of how the universe evolved in its earliest moments. Adding to this cosmic unease is another void-like anomaly, the cold spot in the cosmic microwave background, CMB, 8 billion years, 8 billion light years, 0.00015 degrees Celsius colder than expected. But on the scale of the CMB, such a difference is profound. Some researchers have proposed that the cold spot could be the imprint of another universe colliding with our own, a cosmic bruise from a primordial interaction between bubble universes in a vast multiverse. Others suggest it might be the shadow of a supervoid, an enormous region of emptiness so large that light passing through it loses energy, creating the observed cold region in the CMB. Either explanation forces us to confront unsettling possibilities about the nature of our universe and its relationship to what might lie beyond. The existence of these great cosmic emptinesses raises another disturbing possibility, that the tendency toward nothingness is the universe's natural state, and the matter we observe, the stars, planets, galaxies, and life itself, represents a temporary deviation from cosmic emptiness. As the universe continues to expand at an accelerating rate, driven by the mysterious force we call dark energy, the spaces between galaxies grow ever larger. Galaxies beyond our local group are already receding from us faster than the speed of light due to the expansion of space itself, meaning their light will never reach us. In the far future, any civilization arising in what remains of the Milky Way would observe a night sky almost entirely devoid of other galaxies, an artificial void created by the relentless expansion of space-time. This eventual fate, an observable universe containing only a few gravitationally bound galaxies surrounded by infinite darkness, represents the ultimate triumph of cosmic emptiness. The horror lies not just in the physical isolation, but in the loss of knowledge. Future astronomers would have no way to detect the cosmic microwave background, no evidence of distant galaxies, no means of inferring the Big Bang or the true age and extent of the universe. They would be cosmic castaways, surrounded by an ocean of emptiness with no shoreline in sight. The psychology of emptiness has always troubled the human mind. We evolved in environments rich with stimuli, forests teeming with life, savannas with visible horizons, night skies filled with stars. Complete emptiness represents not just the absence of these familiar reference points, but a fundamental challenge to how we construct meaning. Horror literature often exploits this discomfort, from the empty corridors of haunted houses to the boundless voids of cosmic horror stories. The terror comes not from what is present, but from what is absent, and from the possibility that something might suddenly emerge from that nothingness. This psychological response to emptiness may explain why cosmic voids disturb us on a level beyond their scientific implications. They represent a kind of existential threat, not to our physical survival, but to our ability to comprehend and categorize our surroundings. A void cannot be mapped in detail, cannot be broken down into recognizable patterns or structures. It resists our fundamental cognitive drive to impose order on chaos, to find signal within noise. In the face of such profound emptiness, our minds struggle to maintain their bearings. The horror of cosmic voids also stems from their apparent permanence. Unlike many astronomical phenomena that change over time, stars that explode, galaxies that collide, planets that migrate, voids endure. Once formed, they tend to become more pronounced as the universe ages and expands. The matter that evacuated these regions is unlikely to return, drawn away by the gravitational pull of surrounding structures and the overall expansion of the universe. In this sense, cosmic voids represent not just empty regions, but one-way doors in the evolution of cosmic structure, areas that, once emptied, remain vacant for all of cosmic future. Adding another layer to this cosmic dread is the role of dark matter, the invisible substance that makes up approximately 27% of the universe's mass energy content. Dark matter interacts with normal matter only through gravity, neither emitting nor absorbing light. Yet its gravitational influence shapes the formation of cosmic structures, including voids. Computer simulations suggest that dark matter forms a cosmic web of filaments and sheets, with ordinary matter following these invisible pathways. The voids we observe are the spaces between the dark matter scaffold, meaning that what appears empty to our telescopes may in fact be structured by forces and materials we cannot directly detect. This realization introduces a particularly unsettling thought. We may be fundamentally incapable of truly perceiving the nature of cosmic voids. Our instruments detect electromagnetic radiation, light across various wavelengths, but this reveals only the distribution of ordinary matter. If the true structure of the universe is determined primarily by dark matter, then our maps of cosmic voids are like shadows on a wall, two-dimensional projections of a more complex reality we cannot directly observe. We might be surrounded by intricate dark matter structures completely invisible to us, living in what we perceive as emptiness, but is actually teeming with an alien form of matter. The Eridanus supervoid represents another enormous region of emptiness, spanning roughly 1 billion light-years. This supervoid aligns with a puzzling feature called the CMB cold spot, mentioned earlier. Some cosmologists have proposed that this alignment is not coincidental. The supervoid might be causally connected to the temperature anomaly, perhaps through a physical mechanism known as the integrated Sachs-Wolf effect, which describes how photons gain or lose energy as they travel through changing gravitational potentials. But the size of the Eridanus supervoid, like that of the Bootes void, challenges our understanding of how such structures could form within the age of the universe. Computer simulations of cosmic evolution struggle to produce voids of this magnitude through known physical processes, suggesting either that our models are incomplete or that something extraordinary occurred in these regions. Perhaps most disturbing is the growing evidence that the universe is not just peppered with voids, but is primarily composed of them. As our surveys of the cosmos become more comprehensive, astronomers have discovered that the distribution of galaxies resembles a sponge-like structure with dense filaments and walls surrounding vast bubbles of emptiness. By volume, voids dominate the cosmos. The galaxy-rich regions that we instinctively focus on, the bright nodes and filaments where stars form and planets evolve, represent a minority of the universe's volume. This realization inverts our intuitive understanding of cosmic structure. Rather than thinking of voids as empty spaces between galaxies, we should perhaps view galaxies as thin boundaries between voids, matter compressed into filaments and walls by the expansion of nothingness around them. In this perspective, emptiness is not the exception, but the rule, and the matter we detect with our telescopes is merely the residue left behind as voids expand and merge. The local void, a relatively small cosmic emptiness adjacent to our local group of galaxies, provides a more immediate example of how these structures influence our cosmic neighborhood. Spanning approximately 150 million light-years, the local void appears to be expanding, pushing against our galaxy group. This expansion contributes to the peculiar motion of the Milky Way through space, as our galaxy is simultaneously drawn toward the massive Virgo cluster in one direction while being repelled by the expanding local void in another. This cosmic push-pull illustrates how voids are not passive features, but active players in the evolution of structure. They exert negative gravity, not a repulsive force in the conventional sense, but the absence of the attractive force that would exist if they contained the expected amount of matter. This negative gravity contributes to the complex dance of galaxies through space, influencing their trajectories and potentially their internal evolution. For civilizations like ours, poised at the edge of both knowledge and cosmic structure, these voids represent both a scientific puzzle and an existential challenge. They remind us that the universe does not conform to human expectations of fullness or purpose. The predominance of emptiness suggests a cosmos fundamentally indifferent to the rare pockets of complexity that emerge within it. Islands of matter and energy, temporarily resisting the tide of nothingness that surrounds them. As we gaze into these great emptinesses, we cannot help but feel a primal unease, a recognition that our existence runs counter to the universe's apparent preference for void. We are improbable collections of matter and energy, achieving temporary complexity against the cosmic current flowing toward eternal darkness and dissolution. The horror of the void is not just the terror of emptiness, but the suspicion that emptiness, not fullness, represents the natural state toward which all things ultimately return. And yet, paradoxically, It is precisely the existence of these vast emptinesses that has allowed complexity to emerge. Without the voids between galaxy filaments, matter would be too evenly distributed to form distinct structures. The same cosmic processes that create enormous bubbles of nothing also compress matter along their boundaries, triggering star formation and the eventual development of planetary systems. Our existence depends on the very voids that seem to deny the importance of matter and energy. As we prepare to leave the cosmic void behind and venture into other terrifying aspects of the universe, remember that emptiness represents only one form of cosmic horror. While the void threatens us with nothingness and isolation, other phenomena menace us with unimaginable energies and unstoppable forces. In the cold emptiness between galaxies, at least, we find silence and stillness. But elsewhere in the cosmos, violence reigns on scales that dwarf our comprehension. Among these violent cosmic phenomena, few are more unsettling than the silent wanderers of interstellar space, massive planets ejected from their star systems, doomed to eternal darkness as they drift through the void without a sun to orbit. These are the rogue planets, cosmic outcasts carrying their frozen surfaces through the endless night, and they represent our next encounter with the universe's darkest secrets. Imagine a world without a sun, no sunrise, no sunset, just eternal night stretching in all directions. No warmth radiates from above, no seasons mark the passage of time, no light penetrates the thick atmosphere that might still cling to its frozen surface. This is the fate of a rogue planet, a world cast adrift in the vast darkness between stars, doomed to wander the galaxy alone for billions of years. And the most terrifying part? These nomadic worlds may be far more common than we once believed. Rogue planets, also called free-floating, nomad, or unbound planets, are planetary mass objects that orbit the galaxy directly, untethered to any star. Unlike the Earth, which follows a predictable path around our Sun, receiving its life-giving light and warmth, these orphaned worlds drift through the interstellar void, their surfaces locked in temperatures approaching absolute zero, their atmospheres potentially condensed into solid layers of frozen gases. The very existence of these wandering worlds challenges our traditional understanding of planetary formation. For decades, astronomers believed that planets formed exclusively within the protoplanetary disks surrounding young stars, disks of gas and dust that gradually coalesce into orbiting worlds. But if planets form around stars, how do they end up alone in the darkness of interstellar space? The answer lies in the violent dynamics of young star systems. When planets form around a star, they don't emerge in perfectly stable orbits. Instead, they engage in a gravitational dance, pulling and pushing on each other as they settle into their final configurations. In some cases, this celestial choreography goes catastrophically wrong. A close encounter between two massive planets can send one of them on a trajectory that ejects it from the system entirely, flinging it into the interstellar void. This process is not merely theoretical. Computer simulations of planetary system formation regularly produce scenarios where planets are ejected. In fact, some models suggest that for every planet that remains in a stable orbit around its parent star, one or two might be launched into interstellar space. If these models are correct, our galaxy could contain hundreds of billions of rogue planets, potentially more numerous than the stars themselves. The revelation that these homeless worlds might outnumber stars fundamentally alters our conception of our galaxy. The Milky Way might not be primarily a collection of stars with occasional planetary systems, but rather a vast sea of wandering planets, punctuated by the comparative rarity of starlight. Between each pinpoint of light we observe in the night sky could lurk dozens of invisible worlds, silently drifting through the darkness. Detecting these rogue planets presents an enormous challenge precisely because they emit almost no light of their own. Unlike stars, which announce their presence with brilliant fusion reactions, planets are visible only by the starlight they reflect or the minimal heat they radiate. Without a nearby star to illuminate them, rogue planets become nearly invisible to conventional astronomical observations. Despite these difficulties, astronomers have developed ingenious methods to detect these cosmic wanderers. One of the most successful techniques utilizes gravitational microlensing, the temporary brightening of a background star when a massive object passes between it and Earth. The gravity of the intervening object bends and magnifies the starlight, creating a distinctive brightening pattern. If this lensing object is a star with planets, the planets create small deviations in this pattern. But sometimes, microlensing events occur with no visible star causing them, suggesting the presence of a lone planet drifting through space. Through such observations, scientists have confirmed the existence of several rogue planets, though the total count remains small due to the difficulty of detection. One of the most famous, CFB-DSIR 2087-0334, writing out the numerical designation as you requested, appears to be a gas giant 4 to 7 times the mass of Jupiter, wandering alone roughly 100 light-years from Earth. Its surface temperature, estimated at around 430 degrees Celsius, suggests it is relatively young, perhaps only 50 to 120 million years old. Over time, it will continue to cool, its atmosphere gradually freezing as it drifts through the cosmic night. Even more unsettling are the discoveries of Earth-sized rogue planets. While gas giants like Jupiter can retain their internal heat for billions of years, smaller rocky worlds cool much more quickly. An Earth-like world ejected from its star system would see its surface temperature plummet to nearly -270 degrees Celsius, just a few degrees above absolute zero. Any oceans would freeze solid within years, and even gases like nitrogen and oxygen would eventually condense into liquid, then solid form. The sheer number of these wandering worlds raises a disturbing possibility. Could one of them be heading toward our solar system right now? The space between stars is vast, making collisions extremely unlikely. The average distance between stars in our galactic neighborhood is about 4 light-years, creating enormous empty regions where wandering planets could drift for eons without approaching another star system. If a rogue gas giant several times the mass of Jupiter were to enter our solar system, the gravitational consequences could be catastrophic. Such an intruder could distort the orbits of existing planets, potentially ejecting smaller worlds like Earth from the solar system or sending them crashing into the Sun. It might capture some of our planets as moons or break apart the delicate ring system of Saturn. The particular outcome would depend on the rogue planet's mass, velocity, and the specific trajectory of its approach, but none of the scenarios paint a promising picture for the continued habitability of Earth. Even a more distant encounter could prove disastrous. A rogue planet passing through the Oort Cloud, the spherical shell of icy objects at the outer edge of our solar system, could dislodge countless comets, sending them on trajectories toward the inner solar system. This cometary shower would dramatically increase the probability of a major impact event on Earth, potentially triggering a mass extinction similar to the one that eliminated the dinosaurs 66 million years ago. How much warning would we have of such an approach? Unfortunately, less than might be comfortable. Rogue planets emit very little light or heat, making them difficult to detect until they're relatively close. A large gas giant might be spotted several decades before its arrival, while a smaller, Earth-sized rogue could remain invisible until just years before encounter. This limited warning time would leave humanity with few options for mitigating the threat. Perhaps equally unsettling is the fate that would befall a living world ejected from its star system. Imagine an Earth-like planet teeming with life, suddenly torn from its orbit and cast into the interstellar void. As the planet drifts away from its sun, temperatures would begin to fall. Plants would die first as photosynthesis became impossible, followed quickly by animals dependent on those plants for food. Atmospheric circulation would slow as the energy input from the star diminished, leading to increasingly extreme weather during the planet's final illuminated days. Within weeks, the oceans would begin to freeze from the poles inward. Within months, even the tropical regions would be locked in ice. As surface temperatures plummeted toward absolute zero, the atmosphere itself would begin to condense, with oxygen and nitrogen raining down as liquids before freezing solid on the surface. Within a few short years, a once vibrant biosphere would be reduced to a silent, frozen wasteland, drifting through the cosmic darkness. But could life persist on such a world? Remarkably, some scientists believe it might. Deep beneath the frozen surface of a rogue planet, geothermal heat from radioactive decay in the planet's core could maintain pockets of liquid water. On Earth, we've discovered microbial ecosystems that survive without sunlight. deriving energy from chemical reactions in hydrothermal vents or subsisting on the slow consumption of ancient organic matter. Similar organisms might endure in the subsurface oceans of a rogue planet, perhaps for billions of years after its ejection. This possibility, life persisting in the darkness between stars, presents one of the most haunting images in astrobiology. Imagine intelligent beings evolved to live in the perpetual blackness of subsurface oceans, never seeing stars, never knowing that their world drifts through a vast cosmos filled with light and other worlds. Their entire universe would be the limited volume of their liquid domain, bounded by ice above and rock below. What cosmology would such beings develop? What myths would they tell about their origins? Would they ever discover the true nature of their circumstance? The notion becomes even more poignant when we consider that rogue planets might be capable of transferring life between star systems. A world ejected from one system could, after eons of wandering, be captured by the gravity of another star. If microbial life survived the interstellar journey in deep subsurface environments, it could potentially seed this new system, a process astrobiologists call panspermia. In this way, rogue planets might serve as both destroyers and creators of habitable conditions, agents of cosmic extinction, and vectors for the spread of life across the galaxy. Recent research has suggested another intriguing possibility. Some rogue planets might not be so dark and cold after all. Gas giants ejected from their star systems while still young could generate significant internal heat through gravitational contraction and might retain thick, insulating atmospheres. These conditions could keep their surfaces relatively warm for billions of years. Not warm enough for liquid water, perhaps, but potentially sufficient to maintain exotic biochemistries based on liquid methane or ammonia. Even more surprisingly, a rogue planet with a thick hydrogen atmosphere could experience a powerful greenhouse effect, potentially keeping temperatures high enough for liquid water to exist. Such a world, wandering between the stars, might harbor an entire ecosystem, dependent not on starlight, but on geothermal energy percolating up from below, supporting organisms that never evolved to utilize photosynthesis. The existence of potentially habitable rogue planets further complicates our search for life beyond Earth. Traditional approaches focus on the habitable zone around stars, the orbital region where a planet could maintain liquid water on its surface. But if life can exist on planets without stars, the habitable territory in our galaxy expands dramatically. We might need to broaden our search criteria to include these cosmic wanderers drifting through the darkness. However, detecting life on a rogue planet would be extraordinarily challenging. Without the benefit of transiting in front of a star, we cannot easily analyze the atmospheric composition of these worlds as we can with orbiting exoplanets. Their faint thermal emissions provide limited information about surface conditions, and their potentially vast numbers make systematic investigation daunting. We might be surrounded by life-bearing worlds floating through interstellar space, yet remain utterly unaware of their biological riches. The 2016 discovery of Proxima Centauri b, an Earth-sized planet orbiting our nearest stellar neighbor, highlighted another disturbing aspect of rogue planets: their potential role in disrupting established planetary systems. Computer models suggest that Proxima b may not have formed in its current location, but rather in a more distant orbit before being pushed inward by the gravitational influence of a passing object, possibly a rogue planet. This scenario reminds us that even a non-collision encounter with a wandering world could dramatically alter a planet's orbit, potentially rendering a habitable world uninhabitable, or vice versa. Our own solar system bears potential scars from such encounters. The unusual tilt of Uranus, which rotates nearly on its side, might have resulted from a collision with a rogue planet in the distant past. The scattered disk objects beyond Neptune, including the dwarf planet Eris, follow eccentric orbits that could have been shaped by the gravitational influence of a passing rogue. Even the hypothesized Planet 9, whose existence has been inferred from the aligned orbits of several trans-Neptunian objects, might be a captured rogue planet rather than a native member of our solar system. The Schultz's star system provides a concrete example of a close encounter. 8 light-years of the Sun. The passage likely disturbed the orbits of numerous comets, potentially sending some on trajectories that will bring them into the inner solar system, thousands or tens of thousands of years in the future. If a relatively faint star system, could approach so closely in the geologically recent past, it seems plausible that rogue planets, darker and more difficult to detect, might make similarly close approaches with some regularity. In 2021, astronomers announced the discovery of what might be the smallest free-floating planet found to date, a world roughly the mass of Earth wandering through the Milky Way. Unlike massive gas giants, which can more easily be detected through their gravitational influence or residual heat, finding Earth-sized rogues represents a significant technical achievement. This discovery suggests that small rocky worlds might be as common among the rogue planet population as they are in star-orbiting systems. The implications are staggering. If Earth-mass rogue planets are indeed numerous, space between stars might be filled with frozen versions of worlds like our own, planets that once harbored liquid water, complex chemistry, perhaps even life, before being cast into the interstellar void. The galaxy could be littered with the frozen tombs of extinct biospheres, each one preserving the record of evolutionary paths cut short by cosmic catastrophe. Or perhaps more optimistically, some of these wandering worlds might carry the seeds of life between the stars, dormant microbes capable of surviving thousands or millions of years in suspended animation, waiting for their frozen world to be captured by a new star and thawed back into habitability. Life, in this view, might be a persistent phenomenon that survives even planetary ejection events, using rogue planets as vessels to navigate the vast gulfs between suitable habitats. The 2019 discovery of the interstellar comet 2I Borisov, spelled out as requested, provided a glimpse of how objects from other star systems regularly pass through our neighborhood. While not a rogue planet, this visitor from beyond our solar system demonstrated that interstellar space is far from empty. Every star system likely ejects numerous comets, asteroids, and yes, occasionally planets, creating a galaxy-wide exchange of material that has continued for billions of years. This cosmic exchange raises a profound question. Could Earth itself become a rogue planet someday? While our current orbit around the Sun is stable, the long-term future of our solar system contains many uncertainties. 5 billion years, the Andromeda Galaxy will collide with the Milky Way, potentially disrupting the orbits of countless star systems. Even before this event, passing stars or massive interstellar clouds could gravitationally perturb our solar system. And on an even longer timescale, as the Sun exhausts its hydrogen fuel and expands into a red giant, its reduced mass could weaken its gravitational hold on the outer planets. If Earth were to become a rogue planet, cast into interstellar darkness either through gravitational perturbation or the death of the Sun, what traces of our civilization might endure the freezing darkness? Most surface structures would be crushed under ice sheets as the oceans froze. But objects in stable orbits, like our geostationary satellites, might continue to circle the planet for billions of years, preserved in the vacuum of space, silent monuments to a once warm world that harbored life and even intelligence. The concept of rogue planets forces us to reconsider our place in the cosmic order. We tend to imagine planets as subordinate to stars, orbiting them, warmed by them, defined by their relationship to them. But if rogue planets outnumber stars in our galaxy, perhaps this star-centric view is backward. Perhaps planets are the primary objects of the Milky Way, with only a minority finding themselves gravitationally bound to stars. In this perspective, Earth is not typical but exceptional, a planet that won the cosmic lottery by maintaining a stable orbit around a reliable star. This reframing highlights the precariousness of our existence. Earth's habitability depends on its precise, stable relationship with the Sun, a relationship that could be severed by gravitational encounters with passing objects. The threat is remote in human timescales, but becomes increasingly probable over astronomical time. The wandering worlds between the stars serve as a reminder that planetary systems are not permanent features, but temporary arrangements in a dynamic, ever-changing galaxy. As technology advances, we may someday develop the capability to detect rogue planets with greater ease, perhaps using infrared space telescopes or gravitational microlensing surveys of unprecedented sensitivity. Such discoveries would help establish the true population of these nomadic worlds and clarify their role in galactic evolution. We might determine whether Earth-like rogues are common or rare, whether life-bearing planets frequently become cosmic wanderers, and whether our solar system has had close encounters with such objects in the past. Until then, these dark wanderers will continue their silent journeys through interstellar space. Primordial worlds ejected during the chaotic formation of their birth systems, former habitable planets cast into eternal winter by gravitational perturbations, massive gas giants slowly cooling as they drift between the stars. They move through the galaxy like cosmic ghost ships, carrying their frozen cargoes of what might have been or what might yet be. As we contemplate the horror of these wandering worlds of doom, we should remember that they represent just one class of extreme environment in our universe. While rogue planets embody the terror of isolation and frozen darkness, other worlds face different cosmic nightmares. Planets locked in orbit around stars so close that their surfaces melt into magma oceans. Worlds where glass rains from the sky, planets being slowly devoured by their expanding suns. These are the nightmares of exoplanets, and they represent our next venture into the universe's darkest secrets. If the darkness between stars harbors the frozen nomads we call rogue planets, the regions around stars contain terrors of an entirely different kind. These are the exoplanets, worlds orbiting stars other than our Sun, and since the first confirmed discovery in 1992, astronomers have catalogued thousands of them. But far from finding duplicates of our familiar solar system, we've discovered a menagerie of cosmic nightmares that challenge our understanding of what a planet can be. These are not the gentle, life-nurturing worlds like Earth. They are extreme environments where the very laws of physics seem bent toward creating the most hellish conditions imaginable. Let us begin our tour of these planetary horrors with perhaps the most infamous, HD 189733b. A gas giant roughly the size of Jupiter orbiting a star about 64 light-years from Earth. Discovered in 2005, this world initially seemed unremarkable, just another hot Jupiter orbiting close to its parent star. But in 2007, astronomer Heather Knutson and her team used the Spitzer Space Telescope to create a temperature map of the planet's atmosphere, revealing a world of truly nightmarish conditions. HD 189733b orbits its star at a distance of just 3 million kilometers, about 7 times closer than Mercury orbits our Sun. This proximity means the planet is tidally locked, with one side perpetually facing the scorching star, while the other faces the darkness of space. Surface temperatures on the day side reach a blistering 1,200 degrees Celsius, hot enough to melt silver, gold, or copper. But it's not just the heat that makes this world terrifying, it's the weather. The temperature difference between the day and night sides of HD 189733b creates ferocious winds that rage at speeds of up to 8,700 kilometers per hour, about 7 times faster than the speed of sound on Earth and twice the speed of Earth's most destructive tornadoes. These hypersonic winds carry something far worse than rain or snow: glass. The atmosphere of HD 189733b contains silicate particles that, in the extreme heat of the day side, vaporize into gas. As these silicate vapors are carried by the raging winds to the slightly cooler night side, they condense into tiny shards of glass, creating storms of razor-sharp particles that whip horizontally around the planet at supersonic speeds. Imagine standing on the surface of such a world, assuming some form of protection against the crushing pressure and extreme heat. The sky would glow with the brilliant light of the nearby star, taking up a significant portion of the horizon. The atmosphere, thick with clouds of vaporized rock and metal, would shimmer with an oily iridescence. And then the wind would hit you. Not a gentle breeze, but a hypersonic blast carrying countless microscopic daggers of molten glass, scouring everything in its path. No surface would remain unpolished. No structure would stand for long against this perpetual planet-wide sandblasting from hell. If HD 189733b represents a nightmare of wind and glass, then our next stop, Kepler 70b, embodies the horror of unimaginable heat: 6 million kilometers. The planet's surface temperature reaches an almost incomprehensible 6,800 degrees Celsius, hotter than the surface of many stars, including our Sun. At this temperature, iron, titanium, and aluminum would not just melt but vaporize, existing as metallic gases in the planet's atmosphere. The most astonishing feature of Kepler 70b is that it's being gradually vaporized by its star. The extreme heat strips away the planet's outer layers, creating a comet-like tail of evaporated planetary material stretching out behind it. Astronomers estimate that the planet loses mass at a rate of about 10 circumflex 10 to 10 circumflex 11 grams per second, equivalent to a mountain-sized chunk being eaten away every year. Given enough time, the entire planet may eventually evaporate, leaving nothing but a ghostly trail of gas as evidence it ever existed. The surface of Kepler 70b, if such a thing can be meaningfully defined on a world where rock exists as vapor, would present a scene from the most fevered cosmic nightmare. The nearby star would dominate the sky, its gravitational pull so strong that the planet itself would be distorted into an egg-like shape. The atmosphere would glow with the light of vaporized metals, creating a perpetual twilight even on the side facing away from the star. And everywhere, the heat would be beyond lethal, not just burning but disintegrating any complex molecules, reducing everything to a soup of ionized gas. Moving from heat to pressure, we encounter Gliese 571c, a super-Earth orbiting a red dwarf star about 20 light-years from Earth. Discovered in 2007, this world has about 5 times the mass of Earth, but is likely similar in size, resulting in a surface gravity nearly twice that of our home planet. But it's not the gravity that places Gliese 571c among the nightmare worlds. It's the composition. Based on its density, scientists believe Gliese 571c might be composed largely of diamond. The planet likely formed from carbon-rich material, and the intense pressure in its interior would be sufficient to compress carbon into diamond. Some have dubbed it the Diamond Planet, conjuring images of a glittering, crystalline world of unimaginable wealth. But this gemstone planet would be no paradise. With surface pressures likely dozens or hundreds of times that of Earth's atmosphere, and temperatures reaching several hundred degrees Celsius, the conditions would crush and roast any unprotected visitor. The diamond composition would make the planet extraordinarily stiff and unyielding, with little geological activity to recycle materials or moderate conditions. Instead of a vibrant, dynamic world like Earth, Gliese 571c would be a dense, scorching, immovable sphere of crystallized carbon. Beautiful perhaps from a safe distance, but a realm of extreme pressure and heat up close. If Gliese 571c represents the horror of pressure, then WASP-12b embodies the terror of cosmic destruction on a planetary scale. This gas giant, discovered in 2008, orbits its star at a distance of just 2 million kilometers, completing an orbit every 26 hours. The star's gravitational pull has stretched the planet into an egg shape, and the extreme proximity means WASP-12b is literally being torn apart before our instruments. The star's gravitational forces pull more strongly on the side of the planet facing it than on the far side, creating a difference in force that stretches the planet along the star-planet axis. Material from the planet's outer layers is pulled away, forming a disk of gas around the star. Current estimates suggest WASP-12b loses mass at a rate of about 10 circumflex 12 grams per second, meaning the entire planet may be consumed within about 10 million years, a mere blink in astronomical time. Witnessing the death of WASP-12b from a theoretical vantage point near the planet would present one of the most terrifying astronomical spectacles imaginable. The parent star would fill much of the sky, its gravitational pull visibly distorting the planet beneath your feet. The atmosphere would be in constant, violent motion as gas was stripped away into space. The ground itself, if a gas giant can be said to have a ground, would tremble and shift as tidal forces reshaped the entire world. And all the while, the knowledge that the very planet was disintegrating, that in cosmic terms its remaining lifespan was vanishingly brief, would add an existential horror to the physical one. Other exoplanets present different nightmares. Consider Corot 2b, a gas giant where ferocious magnetic activity creates constant planet-wide lightning storms, thousands of times more powerful than those on Earth. The lightning on this world doesn't just flash occasionally during weather events. It is the weather, an unending electrical apocalypse that engulfs the entire planet. Or ponder the fate of planets orbiting pulsars, the rapidly spinning remnants of exploded stars. PSR 1257 plus 12b was the first confirmed exoplanet, discovered in 1992, orbiting a pulsar about 2,300 light-years from Earth. This world, and others like it, bathes in constant lethal radiation from its stellar corpse host. Each rotation of the pulsar, typically hundreds of times per second, sweeps the planet with a beam of high-energy particles and radiation that would sterilize any surface instantly. These planets, formed either after the supernova that created the pulsar or captured later, exist in a perpetual radiation storm that makes the worst nuclear disasters on Earth seem trivial by comparison. TRES 2b, another gas giant about 750 light-years from our solar system, reflects less than 1% of the light that hits it, making it darker than coal or black acrylic paint. Astronomers believe its atmosphere contains light-absorbing chemicals like vaporized sodium and potassium, or perhaps titanium oxide, the same compound used in some sunscreens. The result is a world of almost perfect blackness, a sphere of darkness in space so black that it's nearly invisible against the cosmic background, detectable mainly by its gravitational effects on its star. One of the most recently discovered nightmare worlds is K2-141b, a super-Earth that orbits so close to its red dwarf star that its year lasts just 10 hours. The proximity to its star means this planet is likely tidally locked, with one hemisphere experiencing perpetual daylight, while the other remains in eternal night. But unlike more moderate tidally locked worlds, where life might find a comfortable zone in the twilight band between hemispheres, K2-141b offers no such sanctuary. Its dayside temperature is estimated at 800 degrees Celsius or higher, sufficient to melt aluminum. Meanwhile, the nightside might be hundreds of degrees cooler, creating temperature gradients and weather patterns of unimaginable violence. The discovery of these extreme worlds has forced astronomers to expand their understanding of what conditions a planet can endure. We once imagined that planets would generally resemble those in our solar system, existing at relatively comfortable distances from their stars, with moderate temperatures and well-behaved atmospheres. The reality has proven far more diverse and far more terrifying. Consider the case of HD 209458b, a gas giant about 150 light-years from Earth. This world experiences temperature swings of over 1,000 degrees Celsius in just 6 hours as it orbits its star. The rapid heating and cooling as different sides of the planet face the star create weather patterns of extraordinary violence, with storms that would make Earth's most destructive hurricanes seem like gentle breezes by comparison. Or take HAT P7b, where astronomers have detected winds that change direction depending on the time of day. In the morning, the winds blow from the night side to the day side. In the evening, they reverse direction. These daily reversals create turbulence and storm systems that encompass the entire planet, with wind speeds reaching thousands of kilometers per hour as different atmospheric layers move in opposing directions. The more we look, the more planetary nightmares we discover. OGL 2005 BLG 390LB orbits so far from its star that its surface temperature is estimated at -220 degrees Celsius, cold enough to freeze nitrogen into a liquid. At such temperatures, any atmosphere would condense onto the surface as solid ice, creating a world of frozen gases with no liquid water and no possibility of Earth-like life. Conversely, 55 Cancri e orbits so close to its star that its surface is likely an ocean of lava. This super-Earth has about 8 times the mass of our planet, but is so hot that its surface rock exists in a molten state. The planet's year lasts just 18 hours, and its surface temperature reaches approximately 2,500 degrees Celsius. Recent observations suggest that 55 Cancri e might have an atmosphere of vaporized rock that condenses into clouds of silicate particles on the slightly cooler night side, essentially raining molten stone onto a surface that's already a sea of magma. The variety of exoplanetary horrors seems limited only by the laws of physics and the imagination of the cosmos. For every nightmare world we've described, dozens more await discovery, each with its own particular brand of cosmic terror. But what makes these planets truly horrifying is not just their extreme conditions, but what those conditions imply about the universe. Our solar system, with its relatively temperate inner planets and stable, nearly circular orbits, appears increasingly to be an exception rather than the rule. The galaxy seems filled with systems where planets migrate inward or outward from their birth positions, where gas giants orbit perilously close to their stars, where worlds are stretched, vaporized, irradiated, or frozen to temperatures approaching absolute zero. The cosmic dice seem loaded against the kind of stable, moderate conditions that allowed life to emerge and thrive on Earth. This realization forces us to confront the possibility that our existence depends on an astronomically unlikely set of circumstances, that habitability as we understand it might be vanishingly rare in the universe. The nightmare exoplanets, with their glass storms and lava oceans and eternal lightnings, might represent the cosmic norm, while Earth represents a statistical anomaly so improbable that it borders on the miraculous. And yet, the night sky is filled with hundreds of billions of stars, each potentially hosting its own planetary system. Even if Earth-like conditions are exceedingly rare, occurring in perhaps one system out of millions, the sheer number of stars in our galaxy suggests that we are not alone, that other temperate worlds must exist among the nightmares. The challenge lies in finding them amid the cosmic horrorscape of more hostile environments. The search for these habitable needles in the galactic haystack drives much of modern exoplanet research. Projects like NASA's Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope aim to identify potentially habitable worlds and characterize their atmospheres, looking for the chemical signatures of life. But for every promising candidate these instruments find, they also reveal dozens more nightmare worlds, expanding our catalogue of cosmic horrors even as they search for cosmic havens. Perhaps the most disturbing implication of the nightmare exoplanets is what they suggest about our own planet's past and future. Earth's current habitable state represents just one phase in its long evolutionary history. Early in our planet's formation, it likely resembled some of the lava worlds we've described, with a molten surface and an atmosphere of vaporized rock. In the distant future, as our sun exhausts its hydrogen fuel and expands into a red giant, Earth may experience conditions similar to those on planets currently being consumed by their stars. The nightmare exoplanets, then, are not just distant curiosities, but potential glimpses of our own world's past and future. Reminders that habitability is not a permanent state, but a temporary condition, a brief window in the long life of a planet during which temperatures, pressures, and chemical compositions align to permit the miracle of life. As our survey of cosmic horrors continues, we turn next from the nightmare worlds themselves to the celestial objects that light them, or sometimes destroy them. For as terrifying as planets can be, they pale in comparison to the violence of their stars, especially those stars entering the final cataclysmic phases of their existence. These stellar time bombs represent the next class of cosmic horror in our journey through the universe's darkest secrets. But before we leave the nightmare exoplanets behind, take a moment to appreciate the seemingly mundane miracle of the world beneath your feet. Earth, with its moderate temperatures, liquid water oceans, and protective but not crushing atmosphere, represents a planetary paradise compared to the hellscapes we've described. The cosmic horrors exist, but so too does our improbable haven. A statistical anomaly perhaps, but one that has permitted the emergence of creatures capable of contemplating the very terrors from which they've been spared. In the vast catalogue of worlds scattered throughout the galaxy, we've found few that resemble home and many that embody our worst planetary nightmares. As we conclude our tour of these distant hells, remember that each one, no matter how extreme its conditions, teaches us something about the physics of planetary formation and evolution. In studying these worlds, we better understand the forces that shaped our own planet and the astronomical good fortune that allows us to exist on a world not dominated by glass rain, lava oceans, or planet-wide radiation storms. The nightmare exoplanets remind us of our cosmic fragility, of how precariously our existence balances on specific conditions that, in the grand scheme of the universe, appear to be rare exceptions rather than common rules. This knowledge should inspire not just horror at what exists elsewhere, but profound gratitude for the temperate world we inhabit, a world that, at least for now, protects us from the more terrifying realities waiting in the darkness beyond our atmosphere. If planets represent the first level of cosmic terror, then stars, the colossal nuclear furnaces that dominate their systems, constitute a deeper order of horror altogether. Stars are not the gentle, stable light sources we might imagine from our comfortable distance from the sun. They are dynamic, violent, and ultimately doomed entities that live out their lives in a continuous state of nuclear catastrophe, balancing on the knife edge between gravitational collapse and explosive radiation pressure. And when that balance finally fails, the results can be among the most energetic and destructive events in the universe. Our own Sun, a relatively mild-mannered star by cosmic standards, releases energy equivalent to about 100 billion nuclear bombs exploding every second. Even this ordinary star occasionally produces coronal mass ejections and solar flares that could devastate Earth's infrastructure if directed toward our planet. But the Sun is a cosmic weakling compared to the true stellar monsters lurking in the darkness. Let us begin with the most dramatic stellar deaths, hypernovae. A typical supernova, the explosion of a massive star at the end of its life, is already almost incomprehensibly violent. A single supernova can briefly outshine an entire galaxy of hundreds of billions of stars, releasing in an instant the energy our Sun will produce over its entire 10 billion year lifespan. But hypernovae make even these cataclysms seem modest by comparison. Hypernovae, also called superluminous supernovae, represent the most extreme stellar explosions astronomers have observed. They can be 10 to 100 times more energetic than regular supernovae, reaching absolute magnitudes of -22 or brighter, approximately 100 billion times more luminous than our Sun. The mechanisms behind these extreme explosions remain somewhat mysterious, but they appear to be associated with the deaths of incredibly massive stars, perhaps 150 to 300 times the mass of our Sun. One leading candidate for hypernovae is a process called pair instability supernova. In stars of sufficient mass, the core temperatures become so extreme that gamma rays spontaneously convert into electron-positron pairs. This conversion reduces the radiation pressure supporting the star against gravitational collapse, causing it to contract and heat further, accelerating the pair production in a runaway process. The result is a complete thermonuclear disruption. The entire star explodes, leaving absolutely nothing behind, not even a remnant neutron star or black hole. Imagine the horror of a civilization orbiting a star doomed to such a fate. As the star enters its final phase, it would brighten dramatically, heating any nearby planets to uninhabitable temperatures. Then, without warning, the star would explode with the energy of billions of normal supernovae. The radiation alone would sterilize all planets in the system instantly. As the blast wave expanded outward at thousands of kilometers per second, it would vaporize anything in its path. Planets, asteroids, comets, all reduced to their constituent atoms and blasted outward into interstellar space. Nothing would survive, not even a fragment of evidence that planets or life had ever existed in that system. But the destruction wouldn't end at the boundaries of the star system. A hypernova can affect regions hundreds or even thousands of light years across. The intense radiation, particularly gamma rays and other high-energy wavelengths, could potentially trigger mass extinction events on planets orbiting other stars in the vicinity. The blast would seed interstellar space with heavy elements forged in the explosion, elements that might eventually form new stars and planets. In this way, hypernovae represent both ultimate destruction and cosmic renewal, the deaths that make new life possible. While hypernovae represent the most dramatic stellar deaths, other types of stars exhibit violence throughout their lives. Among these, none are more terrifying than magnetars, neutron stars with magnetic fields so powerful they defy comprehension. A neutron star forms when a massive star explodes as a supernova, leaving behind a core so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. These objects typically have diameters of only about 20 kilometers, but contain more mass than our Sun. They spin rapidly, completing multiple rotations per second. But magnetars take these already extreme properties and add one more: magnetic fields of unimaginable strength. The magnetic field of a typical magnetar is approximately 10 circumflex 15 Gauss, about 1,000,000,000,000 times stronger than Earth's magnetic field, and 1,000 times stronger than ordinary neutron stars. This field is so powerful that it actually distorts the electron orbitals in atoms, making chemistry as we understand it impossible within thousands of kilometers of the star. At closer ranges, the magnetic field would literally tear apart molecules and atoms by brute force, stripping electrons from their orbits and deforming atomic nuclei into elongated shapes. If you could somehow approach within a few thousand kilometers of a magnetar without being crushed by its gravity, about 100 billion times stronger than Earth's, the magnetic field would erase the information from every credit card and electronic device you carried. Closer still, it would rip the hemoglobin from your blood, essentially killing you by magnetic force alone. And within about 1,000 kilometers, the field would actually tear your body apart, atom by atom, pulling electrons in one direction and nuclei in another. But the most terrifying aspect of magnetars is their unpredictability. These cosmic monsters occasionally produce starquakes, sudden adjustments in their structure that release enormous amounts of energy, primarily in the form of gamma rays. The most powerful magnetar flare ever observed occurred on December 27, 2004, when SGR 1806-20 produced a burst so intense that it saturated all the detectors on every gamma-ray satellite in Earth orbit, despite the fact that this magnetar is located about 50,000 light-years away in the Milky Way galaxy. The energy released in this single magnetar flare exceeded what our Sun produces in 250,000 years. It briefly affected Earth's ionosphere from 50,000 light-years away, which means that if a similar magnetar were located just 10 light-years from us, a comparable flare might destroy our ozone layer, triggering a mass extinction event. Despite its tremendous distance, the flare was so powerful that it could have been detected by our instruments from up to 30 million light-years away, well beyond our galaxy. The existence of objects capable of such violence, scattered like cosmic landmines throughout our galaxy, represents a form of cosmic horror that science fiction has barely begun to address. These are not the cinematic threats of asteroids or even supernova, against which advanced civilizations might conceivably develop defenses. A nearby magnetar flare would arrive at the speed of light, without warning, and deliver extinction-level energy with no possibility of prediction or protection. Another class of stellar extremophiles that inspire cosmic dread are the Wolf-Rayet stars, massive, hot stars in the final stages of their evolution, rapidly shedding mass through powerful stellar winds. These stellar giants, typically more than 20 times the mass of our Sun, burn at surface temperatures exceeding 30,000 degrees Celsius and shine with luminosities millions of times greater than our Sun. The defining feature of Wolf-Rayet stars is their ferocious stellar wind, a continuous outflow of material traveling at speeds of up to 3,000 kilometers per second, or about 1% of the speed of light. These winds are so powerful that they strip away the star's outer hydrogen layers, exposing the helium burning underneath and creating a unique spectral signature that astronomers can identify from Earth. Over its short lifetime of only a few million years, compared to our Sun's expected 10 billion-year lifespan, a Wolf-Rayet star might lose more than half its mass to these winds. The ejected material forms shells and bubbles of superheated gas around the star, creating nebulae of extraordinary beauty when viewed from a safe distance, and extraordinary danger up close. Any planet unfortunate enough to orbit a Wolf-Rayet star would be continuously blasted by high-energy radiation and a hurricane of charged particles. The stellar wind would gradually strip away any atmosphere, leaving the planet's surface exposed to lethal levels of ultraviolet and X-ray radiation. No life as we understand it could evolve or survive in such an environment. And yet, these cosmic blowtorches play a crucial role in galactic evolution, enriching the interstellar medium with heavy elements that will eventually form new stars, planets, and potentially life-bearing worlds. Perhaps the most terrifying stellar phenomena of all, though, are gamma-ray bursts, GRBs, brief but extraordinarily powerful explosions that release more energy in seconds than our Sun will emit in its entire lifetime. These cosmic flashbulbs, the brightest electromagnetic events known to occur in the universe, come in two primary varieties: long-duration bursts associated with the collapse of massive stars, and short-duration bursts likely caused by the merger of compact objects like neutron stars. A typical gamma-ray burst releases energy equivalent to converting the entire mass of a star like our Sun directly into gamma radiation, according to Einstein's famous E=mc2 equation. For a few brief seconds, a gamma-ray burst can outshine the rest of the visible universe combined. The energy is highly focused into two narrow jets that blast outward from the poles of the collapsing star or merging neutron stars at velocities approaching the speed of light. If Earth were caught in the path of a gamma-ray burst from a source even thousands of light-years away, the consequences would be catastrophic. The initial gamma radiation would deplete our ozone layer, exposing the surface to deadly levels of ultraviolet radiation from the sun. This would trigger mass extinctions of land and marine life, particularly affecting the base of the food chain. Photochemical reactions in the atmosphere would produce nitrogen oxides that would cause acid rain and potentially trigger a global cooling event analogous to a nuclear winter. Some scientists have proposed that a previous mass extinction on Earth, perhaps the Ordovician extinction 440 million years ago that wiped out approximately 85% of marine species, might have been triggered by a distant gamma-ray burst. This hypothesis remains speculative, but the mere fact that it's scientifically plausible illustrates the genuine cosmic danger these events represent. What makes gamma-ray bursts particularly terrifying from a cosmic horror perspective is their absolute unpredictability combined with their instantaneous effect. Unlike supernovae, which often show warning signs observable by astronomers, GRBs strike without preamble, arriving literally at the speed of light. By the time we detect a gamma-ray burst, its effects have already reached us. There can be no warning, no preparation, no defense, only the cold statistics of cosmic probability, determining whether our planet happens to lie in the path of one of these lethal beams. Fortunately, gamma-ray bursts are relatively rare events, and the odds of Earth being caught in the narrow beam of one are extremely low. Astronomers estimate that a GRB would need to occur within about 8,000 light-years of Earth, with its beam precisely oriented toward our planet to cause serious damage to the biosphere. Given the distribution of potential GRB progenitors in our galaxy, such an event might occur only once every billion years or so. But over the long history of Earth and the even longer future that awaits our planet, what happens once is essentially guaranteed, just as a 1 in a million annual risk becomes a certainty if you wait long enough. The stellar menagerie contains many other varieties of cosmic violence. Consider R Coronae Borealis stars, which unpredictably fade by several magnitudes when they eject clouds of carbon soot that temporarily block their light. Or luminous blue variables like Eta Carinae, which undergo violent eruptions that can briefly make them the brightest stars in a galaxy. Or Thorne-Zitkow objects, bizarre theoretical stellar chimeras in which a neutron star sits at the center of a red supergiant star, creating unique nuclear reaction pathways impossible in normal stars. Each of these stellar extremophiles represents a different flavor of cosmic violence, a different way in which the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces can combine to create conditions that seem designed to preclude the possibility of life. And yet, paradoxically, it is precisely these violent stellar processes that create the elements necessary for life as we know it. Every atom of carbon in your body, every oxygen molecule you breathe, every atom of calcium in your bones was forged in the nuclear furnace of a star and distributed through space by stellar winds or supernova explosions. The iron in your blood was created in stellar cataclysms. The heavier elements like gold and uranium required even more extreme conditions, perhaps neutron star mergers or particularly energetic supernova. We are, quite literally, made from the debris of stellar violence, the ashes of cosmic catastrophe recycled into the building blocks of life. This profound tension between the life-destroying power of stellar cataclysms and their essential role in creating the preconditions for life lies at the heart of the cosmic horror these objects inspire. Stars are simultaneously creators and destroyers, cosmic mothers and cosmic executioners. The same processes that make life possible also guarantee its eventual extinction. The universe builds with one hand and destroys with the other, indifferent to the consequences for the fragile biological experiments that occasionally emerge in the quieter corners of galaxies. As stars age, they undergo radical transformations that can devastate their planetary systems. Our own sun, currently in the middle of its main sequence lifetime, will eventually exhaust the hydrogen fuel in its core and begin fusing helium. This will cause it to expand dramatically into a red giant, engulfing Mercury and Venus, and possibly Earth as well. Even if our planet narrowly escapes direct consumption, its oceans will boil away and its atmosphere will be stripped by the intense solar wind. A world that sustained life for billions of years will be reduced to a scorched, airless rock. This fate awaits not just Earth, but countless planets throughout the universe. Astronomers have already identified systems that appear to be in the process of being consumed by their expanding stars. The star BD plus 48746, for example, appears to have recently engulfed a massive planet or brown dwarf, temporarily increasing its brightness and expansion rate. The chemical signature of lithium in its atmosphere, an element typically depleted in evolved stars, suggests it has recently digested a planetary companion. Other stars end their lives even more dramatically. Stars with masses between about 8 and 20 times that of our Sun explode as Type II supernovae, leaving behind neutron stars. Those with greater masses collapse directly into black holes, sometimes producing gamma-ray bursts in the process. Each of these stellar fates represents a death sentence for any life in the affected star system. But perhaps the most unsettling aspect of stellar evolution is not the violence of stellar deaths, but the silent, inexorable dimming of the cosmos they represent. Each star that explodes or collapses represents fuel that has been permanently consumed from the universe's finite supply. With each passing billion years, fewer new stars form, using the dwindling reserves of gas not yet incorporated into stars or their remnants. Astronomers estimate that star formation in the universe peaked about 10 billion years ago and has been declining ever since. The most massive, luminous stars exhausted their fuel billions of years before Earth even formed. The universe we observe today is already dimmer, less dynamic, and less violent than the universe of the cosmic past. And the universe of the future will be dimmer still, as fewer new stars ignite to replace those that die. In about 100 trillion years, the last stars will flicker out, leaving a cosmos populated only by stellar remnants, black holes, neutron stars, and white dwarfs, all gradually cooling and fading into darkness. The stellar violence we've described represents not just a threat to hypothetical planetary civilizations, but a fundamental, unavoidable process in the thermodynamic evolution of the universe from order to disorder, from potential to spent energy, from light to eternal darkness. This cosmic eschatology, the study of the ultimate fate of the universe, represents a form of cosmic horror beyond even the most violent stellar explosions. A supernova or gamma-ray burst might destroy a planetary system or even sterilize a section of a galaxy, but the heat death of the universe represents the final extinction of all possibility, the ultimate triumph of entropy over complexity. But we are getting ahead of ourselves. Before the stars fade and the universe grows cold, there are other cosmic horrors to explore. Phenomena even more extreme than supernovae or gamma-ray bursts. As violent as stars can be, they at least obey the conventional laws of physics. They can be observed, measured, and to some extent, predicted. The same cannot be said for our next category of cosmic terror. Black holes, the places where our current understanding of physics breaks down completely, and reality itself seems to unravel at the seams. Unlike stars, which at least provide the light and elements necessary for life, black holes offer nothing but destruction. Gravity wells so deep that nothing, not even light, can escape their grasp. They are cosmic predators, devouring stars, planets, and even light itself. And as we'll discover, they come in sizes ranging from the merely terrifying to the absolutely mind-shattering, from stellar black holes to the supermassive monsters lurking at the centers of galaxies. As we transition from the violence of stars to the existential horror of black holes, remember that we're moving from phenomena that, despite their destructive potential, play a constructive role in cosmic evolution, to objects that represent pure gravitational consumption. Cosmic entropy made manifest, the universe's way of saying that what goes into gravity's deepest wells never comes back out unchanged. At least, that's what we thought until theoretical physics began to suggest otherwise. But those speculations belong to our next chapter. There exists, in the cosmic menagerie of horrors, one phenomenon that stands apart from all others, an entity so extreme that it represents not just a physical threat, but a conceptual one, not merely a danger to life, but a challenge to our understanding of reality itself. This is the black hole, a region of space-time where gravity is so intense that nothing, not light, not matter, not information of any kind, can escape once it crosses the event horizon. Black holes are not merely objects in space. They are ruptures in the fabric of reality, places where the laws of physics as we understand them begin to fray and ultimately break down completely. The concept of a black hole emerged from Einstein's general theory of relativity, though Einstein himself was initially skeptical that such objects could actually exist in nature. The basic principle is deceptively simple. If matter is compressed beyond a certain density, its gravitational field becomes so strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape, hence the term black hole, coined by physicist John Wheeler in 1967 to describe these cosmic traps. But this simplified explanation barely hints at the true horror of black holes. To understand why these objects represent the ultimate cosmic nightmare, we must explore their formation, structure, and the bizarre physics that governs their behavior. Most black holes form from the collapsed cores of massive stars. When a star with more than about 20 times the mass of our Sun exhausts its nuclear fuel, the outward pressure that counterbalanced gravity throughout its life suddenly disappears. The core collapses catastrophically, compressing a mass several times that of our Sun into a volume perhaps just a few kilometers across. The density becomes effectively infinite, the gravitational field near infinite as well, and a black hole is born. The defining feature of a black hole is the event horizon, a boundary in space-time beyond which events cannot affect an outside observer. Once anything crosses this boundary, its fate is sealed. It can never return or send information back to the outside universe. The event horizon is not a physical surface, but a mathematical boundary, a point of no return. It's also a one-way membrane. Information can go in, but none can come out. This property alone makes black holes objects of cosmic dread. Anything that falls into a black hole is, from our perspective, lost forever. A spacecraft, a planet, a star. Once past the event horizon, their fate is to be crushed toward the singularity at the center, their constituent matter compressed to infinite density, their very structure destroyed at the fundamental level. Not just destroyed in the conventional sense of being broken apart, but unmade in a more profound way, reduced to pure energy, with all information about their previous state theoretically erased. I say theoretically because this information paradox, the apparent loss of information when matter falls into a black hole, remains one of the most profound puzzles in theoretical physics. Quantum mechanics insists that information cannot be destroyed, while general relativity implies that information falling into a black hole is indeed lost to the outside universe. This tension between our two most successful physical theories suggests that black holes might be even stranger than we currently understand, perhaps requiring a yet undiscovered theory of quantum gravity to fully explain. But let's set aside these theoretical concerns for a moment and consider what would happen to a human unfortunate enough to fall into a stellar mass black hole. The experience would be defined by two key phenomena: tidal forces and time dilation. Tidal forces arise from the difference in gravitational pull between different parts of an object. As you approach a black hole, the part of your body closest to the black hole experiences a stronger gravitational pull than the part farther away. Imagine your feet being pulled downward with increasingly greater force than your head, stretching your body like taffy, while simultaneously being squeezed inward from the sides. The human body, evolved to withstand Earth's relatively gentle gravitational field, would be torn apart atom by atom as it approached the event horizon of a stellar mass black hole. Your constituent matter would form a thin stream of superheated plasma spiraling into the darkness, joining the accretion disk of material circling the cosmic drain. The second key phenomenon, time dilation, introduces an even more profound horror. According to general relativity, time flows more slowly in stronger gravitational fields, an effect that has been confirmed experimentally, though in much milder conditions than those near a black hole. As you approach the event horizon, this effect becomes extreme. From the perspective of a distant observer, time for you would appear to slow asymptotically, approaching but never quite reaching the moment of crossing the horizon. What this means in practice is that if someone were watching you fall into a black hole, assuming they could somehow observe you despite the absence of light escaping, they would see you move more and more slowly, eventually appearing to freeze at the event horizon, your image becoming progressively redshifted until it faded from view. From their perspective, you would never actually cross the horizon, but would instead remain frozen at its boundary for eternity, or at least until the black hole itself evaporated through Hawking radiation, a process that could take 10 circumflex 67 years or longer for a stellar mass black hole. But from your perspective as the faller, time would continue to flow normally. You would cross the event horizon without experiencing anything special at that boundary and continue your journey inward toward the singularity. Once past the horizon, the geography of space-time changes fundamentally. Every path, every possible future, leads inexorably toward the central singularity. Attempting to move away from the singularity would be as futile as trying to move backward in time. Your destruction becomes not just inevitable, but necessary according to the laws of physics as we understand them. At the center of a black hole lies what we call the singularity, a point of zero volume and infinite density, where space-time itself is infinitely curved. This is not merely a physical extreme, but a mathematical breakdown, a place where our current theories cease to provide meaningful answers. The laws of physics, as formulated in general relativity, predict their own failure at the singularity, suggesting that a more comprehensive theory, perhaps uniting general relativity with quantum mechanics, is needed to describe what happens there. Some theoretical physicists propose that quantum effects might prevent the formation of a true singularity, replacing it with an extremely dense but finite state of matter. Others suggest that singularities might connect to other regions of space-time, forming what we call wormholes. But these remain speculative ideas, beyond our current ability to test experimentally. From an empirical perspective, the interior of a black hole represents the ultimate unknown, a place where our most fundamental theories break down and our most basic intuitions about space, time, and causality fail us. While stellar mass black holes are frightening enough, the universe harbors even more extreme variants. Supermassive black holes, with masses millions or billions of times that of our Sun, lurk at the centers of most large galaxies, including our own Milky Way, 3 million times that of our Sun, and an event horizon larger than the orbit of Mercury. Paradoxically, falling into a supermassive black hole would, in some ways, be less physically traumatic than falling into a stellar mass black hole, because the tidal forces at the event horizon depend on the black hole's density rather than its total mass, and supermassive black holes are less dense than their stellar mass counterparts. You might cross the event horizon of a supermassive black hole without being torn apart. You would, of course, still be doomed, still trapped on a one-way journey toward the central singularity, but you might remain intact slightly longer. This presents an even more disturbing scenario, the possibility of remaining conscious as you fall into a black hole, aware of your situation but unable to escape or communicate with the outside universe. You would be, in a very real sense, eliminated from the causal structure of the universe you once inhabited. Nothing you could do, no signal you could send, would ever reach those you left behind. You would continue to exist, at least for a while, but in a region of space-time, causally disconnected from the rest of reality. At the opposite end of the mass spectrum from supermassive black holes are the hypothetical primordial black holes. Unlike stellar black holes, which form from collapsed stars, or supermassive black holes, which likely grew by accreting matter and merging with other black holes, primordial black holes would have formed in the extreme densities of the early universe, moments after the Big Bang. If primordial black holes exist, they could range in size from microscopic, with masses comparable to a human cell, to massive, with masses comparable to planets or stars. The smaller ones would have mostly evaporated by now through Hawking radiation, but intermediate mass primordial black holes might still exist, potentially even within our solar system. This possibility, that black holes the size of asteroids or planets might be orbiting within our solar system, represents a chilling scenario. Such objects would be extremely difficult to detect directly, as they emit almost no radiation and have gravitational fields significant only at close range. We might infer their existence only through their gravitational effects on other bodies, and even then, only if we were carefully looking for these subtle influences. If such a primordial black hole were to pass through the inner solar system, It could disrupt the orbits of planets or smaller bodies like asteroids and comets, potentially sending some on collision courses with Earth. And if one were to pass through Earth itself, an extraordinarily unlikely but not impossible scenario, it would likely pass straight through our planet without slowing significantly. Its event horizon too small to accrete much matter during the brief passage, but it would leave a trail of gravitational destruction, triggering earthquakes, volcanic eruptions, and potentially worse as it passed through the planet's interior. The possibility of microscopic black holes presents another terrifying scenario. Some speculative theories suggest that high-energy particle collisions, either in cosmic rays or in human-made particle accelerators like the Large Hadron Collider, might create microscopic black holes. These would be so small, with event horizons smaller than an atom, and have so little mass that they would evaporate almost instantly through Hawking radiation, posing no practical threat. But what if our understanding of Hawking radiation is incomplete? What if, for reasons we don't yet comprehend, such microscopic black holes were stable enough to persist and grow by accreting matter? A black hole the mass of a paperclip, with an event horizon a billion times smaller than a proton, could theoretically consume the Earth if given enough time to grow. It would start slowly, accreting individual subatomic particles, but as it grew, its rate of consumption would accelerate exponentially. Eventually, it would devour the planet from within, a cosmic cancer growing in Earth's depths. Physicist Stephen Hawking, who developed the theory of black hole radiation that bears his name, studied this scenario and concluded that it represents no realistic threat. The evaporation rate for tiny black holes should vastly exceed their accretion rate, causing them to disappear in fractions of a second. But like many aspects of black hole physics, this remains theoretical, untested in real-world conditions. The fear of black holes extends beyond their direct physical threat to encompass more abstract existential concerns. Black holes challenge our intuitive understanding of permanence and information. If information truly is lost when matter falls into a black hole, then the universe is not deterministic. The future cannot be predicted from perfect knowledge of the present. This philosophical implication troubles physicists perhaps more than the physical threat of being consumed by a black hole, as it strikes at the heart of how we understand causality and physical law. The theoretical physicist John Archibald Wheeler, who coined the term black hole, captured this existential dread in his famous quotation: "Black holes teach us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but." In other words, black holes remind us that reality itself may be less solid, less reliable than we typically imagine. Recent theoretical work has introduced even more mind-bending possibilities related to black holes. The holographic principle, developed from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary surface. In its most extreme interpretation, this principle implies that our three-dimensional reality might be a projection of information stored on a distant two-dimensional surface, that the universe itself might be a kind of hologram. Similarly, the ER=EPR conjecture, proposed by physicists Leonard Susskind and Juan Maldacena, suggests a connection between quantum entanglement, EPR, and Einstein-Rosen bridges, ER, better known as wormholes. This highly speculative idea proposes that quantum entangled particles might be connected through microscopic wormholes in space-time, effectively tiny black hole pairs. If true, this would imply that quantum mechanics and general relativity, long thought incompatible, might be connected in profound and unexpected ways. These theoretical developments remind us that black holes are not merely destructive cosmic entities, but windows into the deepest questions in physics. They exist at the intersection of quantum mechanics and general relativity, the very small and the very large, in regions where our current understanding breaks down and new physics may emerge. The theoretical possibility of white holes represents another bizarre twist in black hole physics. White holes are the time-reversed version of black holes. While nothing can escape from inside a black hole's event horizon, nothing can enter a white hole's event horizon. Matter and energy can only emerge from a white hole, never go in. According to the mathematics of general relativity, white holes are theoretically possible, but no convincing mechanism for their formation has been identified, and no observations have ever suggested their existence. If white holes did exist, they might be connected to black holes through Einstein-Rosen bridges, forming a black hole/white hole pair connected by a wormhole, a theoretical structure that would allow one-way travel between distant regions of space-time. Such wormholes, if they existed and could somehow be stabilized, would effectively allow a form of one-way time travel into the future. An observer entering a black hole would exit from a white hole potentially billions of years in the future and possibly in an entirely different region of the universe. But these remain mathematical curiosities rather than practical realities. The laws of physics as we currently understand them do not provide a mechanism for the natural formation of traversable wormholes or stable white holes. And even if they did exist, the extreme conditions near their horizons would likely destroy any matter attempting to pass through, a cosmic Charybdis and Scylla, with destruction waiting on either side. What makes black holes particularly terrifying from a cosmic horror perspective is their implacability and inevitability. They cannot be reasoned with, bargained with, or fought against. Their gravitational pull, once you cross the critical threshold, cannot be resisted by any force in the universe. They represent the ultimate cosmic predator, patient, invisible, and inexorable. And yet, black holes are not merely destroyers, but also creators in their own way. The intense radiation and jets emitted by matter falling into black holes can trigger star formation in nearby gas clouds. The supermassive black holes at the centers of galaxies play crucial roles in regulating galactic evolution. And in the distant future, when all stars have burned out and all matter has decayed, black holes may be the last organized structures in the universe, slowly evaporating through Hawking radiation, returning the universe's borrowed energy before the final heat death. This brings us to perhaps the most profound cosmic horror associated with black holes. They remind us of our temporal insignificance. The lifespan of a stellar mass black hole through Hawking evaporation is estimated at around 10 quadrillion years, a time span so vast that it dwarfs not just human history or terrestrial history, but cosmic history itself. 8 billion years is a mere instant compared to the lifespan of a black hole. Even more chillingly, supermassive black holes would persist for about a Google year. That's a 1 followed by 100 zeros, before evaporating completely. By that distant epoch, all stars will have burnt out. All planets will have been ejected from their orbits or consumed. All matter will have decayed into elementary particles, and even protons may have disintegrated through hypothetical decay processes. Black holes would be the last organized structures in a universe otherwise consisting of diffuse, low-energy radiation gradually cooling toward absolute zero, the last embers of a once vibrant cosmos. And what happens after the last black hole evaporates? Current physics offers no clear answer, only the bleak prospect of a universe in which organized structures can no longer form, in which entropy has reached its maximum, and in which time itself may lose meaning without the thermodynamic arrow to define its direction. This is the heat death of the universe, a fate possibly even more terrifying than being consumed by a black hole. Not oblivion, but eternal, meaningless existence in a universe where nothing ever happens and nothing can ever happen again. Yet even this ultimate cosmic fate remains theoretical, contingent on our current understanding of physics, which we know is incomplete. The discovery of dark energy and the accelerating expansion of the universe have already forced revisions to our models of cosmic evolution. Perhaps other discoveries await that will reshape our understanding of the universe's ultimate fate, just as black holes themselves have reshaped our understanding of space, time, and gravity. As we prepare to leave these darkest of cosmic monsters behind, remember that black holes represent not just physical extremes, but conceptual ones, places where our understanding of reality itself begins to break down. They are cosmic question marks, regions where the known laws of physics predict their own failure and point toward a deeper understanding we have yet to achieve. In our next exploration, we'll expand our view from individual objects to entire galaxies, examining the violent processes through which these vast stellar cities grow by consuming their smaller neighbors. For while black holes may devour stars and planets individually, entire galaxies engage in a similar process of consumption on a much grander scale, a cosmic food chain operating over billions of years, wherein the largest structures grow by absorbing their smaller neighbors. This is the phenomenon of galactic cannibalism, and it represents our next encounter with the universe's darkest secrets. If black holes represent the ultimate cosmic predators at the stellar scale, consuming matter one star or planet at a time, then what we are about to explore operates at an even grander level, the consumption of entire galaxies. Galactic cannibalism, the process by which larger galaxies absorb and incorporate smaller ones, represents one of the fundamental mechanisms of cosmic evolution. And unlike many of the horrors we've discussed so far, this one isn't theoretical or safely distant. It's happening right now throughout the universe, and our own Milky Way is an active participant, both as predator and, eventually, as prey. The basic mechanism of galactic cannibalism is deceptively simple. Gravity pulls galaxies toward each other, and when they meet, the larger galaxy's gravitational field disrupts and ultimately absorbs the smaller one. But this clinical description fails to capture the cataclysmic violence involved in such encounters, which unfold over hundreds of millions of years and encompass the fates of hundreds of billions of stars, along with their planets and any life they might harbor. Our own Milky Way galaxy provides ample evidence of its cannibalistic past. Astronomers have identified multiple stellar streams, ribbons of stars with similar properties moving together through the galaxy, that represent the dismembered remains of smaller galaxies and globular clusters consumed by the Milky Way. Each stream tells the story of a once independent stellar system that ventured too close to our galaxy's gravitational field and was slowly torn apart, its stars redistributed into the vast halo surrounding the Milky Way's central disk. One of the most prominent examples is the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy currently in the process of being devoured by the Milky Way. Discovered in 1994, this galaxy has already completed several orbits through the Milky Way's disk, losing stars with each passage as our galaxy's tidal forces strip them away. What we observe today is merely the core of what was once a much larger system, with the lost stars now forming a complex stream that wraps around the Milky Way multiple times like a ghostly scarf. The consumption of the Sagittarius dwarf isn't just an astronomical curiosity. It has had tangible effects on our galaxy. Each time this smaller galaxy passes through the Milky Way's disk, its gravitational influence triggers waves of star formation, like a pebble creating ripples in a pond. Some astronomers believe that the Sagittarius dwarf's passages may have contributed to major episodes of star formation in our galaxy's history, potentially including the formation of our own sun. In this sense, we might owe our existence to an act of galactic cannibalism, a sobering thought that connects our origins to the destruction of another galaxy. The Sagittarius dwarf is far from the only victim of the Milky Way's gravitational appetite. Astronomers have identified at least a dozen significant accretion events in our galaxy's history, with names like the Gaia sausage, also called the Gaia-Enceladus merger, and the Sequoia galaxy. Each represents a once-independent collection of stars, gas, and possibly planets that has been incorporated into our cosmic home. But these past meals are merely appetizers compared to the current feast underway. The Milky Way is currently consuming several smaller galaxies, including the Canis Major dwarf galaxy, the Virgo stellar stream, and various other dwarf spheroidal galaxies that orbit our galactic center as satellites. Each will eventually be fully absorbed, their component stars distributed throughout our galaxy, their unique identities erased by gravitational homogenization. This ongoing process of consumption and assimilation raises a disturbing question. What happens to habitable planets and any life they might harbor when their home galaxy is consumed by a larger one? The answer depends on the specific details of the merger, but is rarely positive for the development or continuation of complex life. In the early stages of galactic cannibalism, as the smaller galaxy begins to feel the tidal forces of its larger neighbor, stars in its outer regions are stripped away first. These stars, suddenly finding themselves in the halo of the larger galaxy, would experience a dramatic change in their cosmic environment. The night sky for any planets orbiting these stars would gradually transform. the familiar constellations of their home galaxy slowly distorting and dispersing as their stellar neighborhood is dismantled by gravitational forces. As the merger progresses, more violent events become likely. The gas clouds common in galaxies begin to collide, compressing and triggering bursts of star formation. These starburst regions represent some of the most active and energetic environments in the universe, with massive stars forming, living and dying in rapid succession. The increased rate of supernova in these regions would fill the interstellar medium with radiation and high-energy particles, potentially sterilizing nearby planetary systems. The central regions of the merging galaxies, where density is highest, experience the most dramatic effects. If both galaxies contain supermassive black holes at their centers, as most large galaxies do, these black holes will eventually spiral toward each other and merge in a cataclysmic event that releases enormous amounts of energy in the form of gravitational waves. In the final moments of such a merger, the power emitted in gravitational waves can briefly exceed the combined electromagnetic output of all the stars in the observable universe. While gravitational waves themselves don't directly damage matter, they pass through planets and people alike with only infinitesimal distortions. The process leading to the black hole merger involves tremendous disruption to the surrounding stellar environment. Stars near the galactic center would be thrown into chaotic orbits, increasing the likelihood of close stellar encounters that could destabilize planetary systems, sending planets careening into their stars or ejecting them into interstellar space as rogue planets. For planets that retain stable orbits around their stars throughout the merger, other threats emerge. The reconfiguration of gas clouds and dark matter halos changes the gravitational landscape of the combined galaxy, potentially exposing previously sheltered regions to cosmic rays and radiation from the galactic center. The altered distribution of mass might also affect the frequency with which stars pass near enough to disturb the Oort Cloud analogues around other stars, potentially increasing the rate of comet showers in formerly stable planetary systems. All of these processes unfold on timescales of millions to billions of years, slow by human standards but rapid in cosmic terms. A technological civilization arising in a galaxy undergoing cannibalism might have enough time to observe and understand what was happening, perhaps even to develop strategies for survival, but would be powerless to prevent the larger process. The feeling would be akin to watching a slow-motion natural disaster unfold over generations, an inexorable cosmic catastrophe governed by the implacable laws of gravitational dynamics. Now, let us turn our gaze from these general principles to a specific case of galactic cannibalism, one that isn't safely distant in space or time, but is instead an inevitable part of our own galaxy's future. 5 million light-years from our galaxy, the closest major galaxy to the Milky Way and the most distant object visible to the naked eye from Earth. Despite this vast distance, Andromeda is moving toward us at about 110 kilometers per second, driven by the mutual gravitational attraction between our galaxies. This approach has been known for decades, but only in 2012 did precise measurements from the Hubble Space Telescope confirm that the encounter will be a direct hit rather than a near miss. As Andromeda approaches, its appearance in Earth's night sky, assuming Earth still exists and still harbors observers, will grow progressively more dramatic. 75 billion years from now, Andromeda will appear significantly larger in the sky. 85 billion years from now, it will dominate the night sky, appearing as a vast, looming presence overhead. 9 billion years, the Milky Way and Andromeda will begin to distort noticeably due to their mutual gravitational interaction, their elegant spiral arms twisting and stretching as the galaxies begin their cosmic dance. The first close approach will occur about 4 billion years from now, with the two galaxies interpenetrating but then moving apart again, like two drops of water that touch but initially fail to coalesce. They will retreat from each other, slowed by their mutual gravitational pull, and then fall back together for a second, closer pass. This gravitational ballet will continue, with the galaxies making multiple passes through each other, each more intimate than the last, until they eventually merge completely into a single elliptical galaxy over the course of the next several billion years. During these passes, the probability of direct stellar collisions remains extraordinarily low. The stars in both galaxies are separated by such vast distances compared to their sizes, that they would mostly pass by each other like ships in the night. But the gas clouds within the galaxies would collide, triggering the bursts of star formation mentioned earlier, and the gravitational interactions between stars would alter their orbits, reconfiguring both galaxies with each pass. What would this look like from Earth? Assuming our planet still exists, a significant assumption, given that the Sun will be entering the later stages of its main sequence lifetime during this period, and will have brightened significantly. The night sky would offer a spectacular and terrifying show. The Andromeda Galaxy would grow from its current appearance as a faint, fuzzy patch to a looming presence that stretches across the entire sky. During the first close pass, observers on Earth's night side would see a canopy of stars surrounding them in all directions as the Milky Way and Andromeda interpenetrate. The increased rate of star formation, triggered by the merger, would create bright blue regions where new stars are being born, contrasting with the redder regions of older stellar populations. Vast tidal tails, streams of stars pulled out from both galaxies by gravitational forces, would stretch across the sky like cosmic streamers. The familiar band of the Milky Way, which has oriented human navigation and mythology for thousands of years, would become distorted and eventually unrecognizable. But these spectacular views would come with potential hazards for any life that managed to survive on Earth into this distant epoch. The increased supernova rate throughout the merging galaxies would raise the average level of cosmic radiation. The gravitational perturbations from the merger could send comets from the Oort Cloud into the inner solar system more frequently, and while the chances of another star passing close enough to directly disrupt Earth's orbit remain slim, they would be significantly higher than they are today. The merger of the Milky Way and Andromeda represents a relatively gentle case of galactic cannibalism, more a mutual amalgamation than a true consumption, given the similar sizes of the two galaxies. More extreme cases occur when a larger galaxy absorbs a much smaller one, or when multiple galaxies collide simultaneously in dense cosmic environments like galaxy clusters. In galaxy clusters, the most massive central galaxies grow through repeated acts of cannibalism, consuming smaller galaxies that venture too close to the cluster's center. These brightest cluster galaxies, BCGs, can contain the stellar mass of hundreds or thousands of former galaxies, all amalgamated into a single massive elliptical system. The central galaxy in the Perseus cluster, for example, has grown to enormous size through this process and continues to consume smaller galaxies that fall toward the cluster's gravitational center. The most extreme environments for galactic cannibalism are found in rich galaxy clusters undergoing mergers themselves. When two galaxy clusters collide, they create a cosmic environment of unprecedented violence. 7 billion light-years from Earth provides a dramatic example of such an event. This system consists of two galaxy clusters that pass through each other at speeds of millions of kilometers per hour, creating shock waves in the intergalactic gas that give the cluster its distinctive appearance. In such environments, galaxies experience extreme tidal forces, ram pressure stripping, where the intergalactic medium acts like a cosmic headwind, stripping away gas from galaxies moving through it, and frequent gravitational encounters with other galaxies. The result is accelerated evolution, with spiral galaxies transformed into ellipticals, star formation both triggered and quenched in different regions, and the overall distribution of matter fundamentally altered. For any intelligent species unlucky enough to evolve in a galaxy within such a cluster, the night sky would offer constant reminders of cosmic violence. Nearby galaxies would appear distorted by tidal interactions, some trailing streams of stars like cosmic tadpoles. The intergalactic medium would glow with X-ray emission from gas heated to millions of degrees by the cluster's gravitational potential, and the overall motion of galaxies within the cluster would be visible over generational timescales, with neighboring galaxies visibly changing position during a single species' history. The process of galactic cannibalism connects directly to another cosmic horror we've discussed: black holes. As galaxies merge, their central supermassive black holes eventually coalesce as well. This process, the merger of black holes with masses millions or billions of times that of our Sun, represents one of the most energetic events in the contemporary universe. The gravitational waves produced in such mergers are so powerful that they distort space-time itself, sending ripples propagating across billions of light years. These black hole mergers also play a crucial role in galaxy evolution. As the supermassive black holes spiral toward each other, they interact with surrounding stars and gas, transferring enormous amounts of energy to them. This energy input can heat the galaxy's gas, preventing it from cooling and forming new stars, a process astronomers call AGN feedback, where AGN stands for active galactic nucleus. Through this mechanism, black hole mergers can effectively shut down star formation in a galaxy, transitioning it from an actively star-forming spiral into a red and dead elliptical galaxy, where few new stars form. The future merger of the Milky Way and Andromeda will eventually lead to the merger of their central black holes as well, 3 million solar masses. When these black holes eventually merge, they will release energy equivalent to converting several sun-sized stars entirely into gravitational waves. Galactic cannibalism also influences the distribution of dark matter, the mysterious substance that makes up about 85% of the matter in the universe, and that we can detect only through its gravitational effects. When galaxies merge, their dark matter halos combine as well, creating larger, more complex distributions. Some theories suggest that the interaction between dark matter halos during galaxy mergers might occasionally create regions of enhanced dark matter density that could be detected by their gravitational lensing effects or by the behavior of stars moving within them. The influence of dark matter on galactic cannibalism adds another layer of cosmic horror to the phenomenon. Most of what happens during a galaxy merger, most of the mass involved, most of the gravitational effects remains completely invisible to us. We see the stars and gas, but the dominant gravitational players lurk unseen, detectable only by their effects on visible matter. It's as if we're watching a puppet show while remaining unaware of the puppeteers or observing the wake of ships we cannot see. This invisible aspect of galactic evolution connects to a broader theme in cosmic horror, the limits of human perception. Much of what happens in the universe, from the quantum fluctuations that might have spawned our cosmos to the dark matter interactions that shape its largest structures, remains inaccessible to our direct senses. We rely on instruments and mathematics to infer these processes, but our intuitive understanding falters when confronted with phenomena that have no analogues in our everyday experience. As we conclude our exploration of galactic cannibalism, it's worth reflecting on the temporal scale of these processes. The current merger of the Sagittarius dwarf with the Milky Way has been ongoing for billions of years and will continue for billions more. The future merger with Andromeda won't begin in earnest for another 4 billion years. These timescales dwarf not just human history, but the entire history of complex life on Earth. And yet, paradoxically, we can observe similar processes happening right now in distant galaxies. When we look at interacting and merging galaxies billions of light years away, we're seeing events that occurred billions of years ago, when the universe was much younger. The light from these distant cosmic collisions has traveled across most of the observable universe to reach our telescopes, allowing us to witness the process of galactic evolution from nearly the beginning of time to the present. This ability to observe events spanning cosmic timescales gives humanity a unique perspective on the universe, one that transcends our brief individual lives and even our species' existence. We can see processes that began before the Earth formed and will continue long after our sun has died. Through our observations and the mathematics we've developed to interpret them, we can trace the history of galactic cannibalism from the early universe to the present and project it into the distant future, including our own galaxy's ultimate fate. But this perspective comes with an existential cost, the recognition of our temporal insignificance. The processes that shape galaxies, that create and destroy the environments where life might arise, operate on timescales so vast that human civilization represents less than an eye blink in cosmic terms. Our entire species might rise and fall multiple times during a single instance of galactic cannibalism. Our achievements and failures alike reduced to cosmic irrelevance by the inexorable march of gravitational dynamics. And yet, the very fact that we can comprehend these processes, that we can trace the history of galactic cannibalism and predict its future course, represents a kind of triumph against cosmic insignificance. We may be brief, but in that brevity, we've achieved understanding. We've looked into the cosmic abyss and instead of turning away, have developed the mathematics and instruments to plumb its depths. As we turn from the consumption of galaxies to our next topic, the mysterious force driving the universe's accelerating expansion, remember that galactic cannibalism represents both destruction and creation. The violence of these cosmic collisions destroys the familiar, but from that destruction emerge new galaxies, new environments, new possibilities for the complex chemistry that might eventually lead to life. The universe builds with one hand and destroys with the other, indifferent to the consequences for beings like us who briefly witness the process. The Milky Way we call home is both predator and prey in this cosmic food chain, having consumed smaller galaxies throughout its history and fated to be consumed, or at least transformed, by its encounter with Andromeda. The atoms in our bodies were forged in ancient stars. The elements that make up Earth were distributed by supernova that might have been triggered by long-forgotten galaxy mergers. We are, in a very real sense, the product of galactic cannibalism, brief arrangements of matter that have temporarily gained consciousness within a process spanning billions of years and trillions of stars. And now, let us turn to a force even more mysterious and potentially more destructive than gravity, the dark energy that drives the universe's accelerating expansion, and that may, in the most distant future, tear apart the very fabric of space itself. This is the dark energy threat, and it represents perhaps the ultimate cosmic horror, the possibility that the fundamental constants of physics might not be constant after all, and that the universe itself might be inherently unstable. We have journeyed through many cosmic nightmares, from the endless voids between galaxies to wandering rogue planets, from hellish exoplanets to exploding stars, from ravenous black holes to cannibal galaxies. But all of these horrors, terrifying as they are, operate within the framework of a relatively stable cosmos. They obey the laws of physics as we understand them, laws that we've spent centuries carefully determining and that form the bedrock of our scientific worldview. But what if the universe itself is fundamentally unstable? What if the cosmic constants we've measured, the laws we've deduced, the equations we've written on blackboards and programmed into computers, what if all of these represent just a temporary configuration, a phase that will eventually give way to something radically different? This is the ultimate cosmic horror suggested by dark energy, a mysterious force permeating the entire universe that pushes space itself to expand at an ever-accelerating rate. To understand the existential dread associated with dark energy, we need to trace the history of how we discovered it and what it implies for the fate of everything we know. The story begins in the late 1990s, when two independent teams of astronomers were using Type Ia supernovae, extraordinarily consistent stellar explosions, to measure the expansion rate of the universe at different epochs in cosmic history. The expectation was simple. Since gravity attracts, the expansion of the universe should be slowing down over time as matter pulls on other matter. But the data revealed something entirely unexpected and profoundly disturbing. The supernovae were fainter than they should have been if the universe's expansion was slowing down. The only explanation that fit the observations was that the expansion of the universe isn't slowing down at all, it's speeding up. Something is pushing space apart, and that push is getting stronger over time. This discovery, which earned a Nobel Prize in 2011, forced cosmologists to confront the possibility that about 68% of the energy content of the universe exists in a form we don't understand and cannot directly detect. This dark energy has no analog in our everyday experience, no parallel in standard physics. It doesn't behave like matter or radiation or any other substance we've studied. Instead, it seems to be a property of space itself, a kind of negative pressure or tension inherent in the fabric of the cosmos. The simplest model of dark energy, known as the cosmological constant, treats it as an intrinsic energy density of empty space that remains constant regardless of how much the universe expands. This idea actually dates back to Albert Einstein, who introduced a similar term into his equations of general relativity to create a static universe, what he later called his greatest blunder, after Edwin Hubble discovered that the universe is in fact expanding. But the cosmological constant has been resurrected to explain dark energy, and the implications are genuinely nightmarish. If dark energy maintains a constant density as space expands, then the total amount of dark energy in the universe increases as the volume of the universe increases. This means that dark energy, unlike matter or radiation, doesn't get diluted by expansion. Instead, it becomes proportionally more dominant over time. In the early universe, matter and radiation were so densely packed that they dominated the cosmos, and dark energy was a negligible factor. Gravity was firmly in control, slowing the expansion that began with the Big Bang. But as space expanded and matter became more diffuse, the constant density of dark energy gave it an increasingly strong influence. About 5 billion years ago, dark energy overtook gravity as the dominant force shaping the universe's evolution, and the cosmic expansion began to accelerate. This acceleration will continue indefinitely under the cosmological constant model. As the universe expands, galaxies will move away from each other at ever-increasing speeds. Eventually, galaxies outside our local group, the gravitationally bound cluster that includes the Milky Way, Andromeda, and several dozen smaller galaxies, will be receding faster than the speed of light due to the expansion of space itself. This doesn't violate Einstein's prohibition against faster-than-light travel, because the galaxies aren't moving through space at those speeds. Rather, the space between them is expanding. It's as if the galaxies are stationary points on an inflating balloon, moving apart not because they're traveling across the balloon's surface, but because the surface itself is stretching. The practical consequence of this expansion is that those distant galaxies will eventually disappear from our observable universe. Their light, traveling through ever-expanding space, will never reach us. Within about 100 billion years, the only galaxies visible from Earth, assuming Earth or any observer still exists, will be those in the local group. All other galaxies will have passed beyond our cosmic horizon, invisible and unreachable even in principle. This isolation represents a kind of cosmic quarantine, a permanent separation of our local galactic neighborhood from the rest of the universe. Any civilization arising after this point would have no way to observe distant galaxies, no way to detect the cosmic microwave background radiation, no way to infer the Big Bang or measure the true age and scale of the cosmos. Their universe would appear to consist of a small cluster of aging galaxies surrounded by infinite, empty darkness. But this scenario, disturbing as it is, represents just the beginning of dark energy's potential threat. Some theoretical models suggest even more extreme possibilities. The Big Rip hypothesis, proposed by physicist Robert Caldwell and colleagues, imagines a form of dark energy that grows not just in total amount, but in density over time. This phantom energy would cause the cosmic expansion to accelerate so dramatically that it would eventually overcome not just the gravitational bonds between galaxies, but those holding individual galaxies, solar systems, planets, and ultimately atoms together. Under this scenario, the end of the universe would unfold in a horrifyingly predictable sequence. First, galaxies outside our local group would disappear beyond the cosmic horizon, as in the standard dark energy model. Then, the accelerating expansion would begin to tear apart the local group itself, with Andromeda and other neighboring galaxies receding beyond our ability to observe them. Next, our own Milky Way galaxy would begin to disintegrate, its stars flying apart as the space between them expanded too rapidly for gravity to hold them together. Our solar system would follow, with the planets flung away from the Sun into the darkness of interstellar, soon to be intergalactic space. The final stages would unfold at the atomic and subatomic levels. The Earth itself would be torn apart, followed by molecules, then atoms, then atomic nuclei. In the last fraction of a second, even the subatomic particles would be ripped asunder as the quantum fields that bind them were overwhelmed by the runaway expansion of space. The Big Rip represents cosmic horror in its purest form, the universe destroying itself from within, the laws of physics as we understand them breaking down completely, and everything we know dismantled piece by piece in a predictable but utterly unstoppable sequence. The fact that serious physicists consider this a plausible scenario, based on our current understanding of dark energy, adds an element of scientific credibility to what might otherwise seem like mere apocalyptic fantasy. How likely is this nightmare? Current observations favor the cosmological constant model over phantom energy, making a big rip less probable than the more gradual isolation scenario described earlier. But our understanding of dark energy remains in its infancy. The accelerating expansion of the universe was discovered less than 30 years ago, and the nature of the force driving it remains one of the greatest unsolved problems in physics. This uncertainty itself represents a form of cosmic horror, the possibility that we might never fully understand the force that will determine the ultimate fate of everything we know. Dark energy operates on scales so vast and over time frames so long that designing experiments to probe its nature challenges the limits of human ingenuity. We're like microbes trying to comprehend plate tectonics, operating at scales of space and time that make direct observation nearly impossible. Alternative models of dark energy introduce other disturbing possibilities. Some theories suggest that dark energy might be a scalar field, similar in some ways to the Higgs field that gives particles their mass, that could change its behavior over time. These quintessence models raise the possibility that dark energy might not be constant after all, but could weaken or strengthen, potentially transitioning between different states as the universe evolves. If dark energy does represent a scalar field, it might exhibit the same kind of symmetry breaking that physicists believe occurred in the early universe, when the fundamental forces separated from one another. This would mean that the cosmos we observe today, with its specific physical laws and constants, represents just one possible phase of the universe, a local minimum in a complex energy landscape that could eventually tunnel or transition to a completely different state. This possibility that the universe could undergo a phase transition similar to water freezing or boiling, but involving the fundamental constants of nature, introduces a form of cosmic instability that makes all other threats seem trivial by comparison. If the values of physical constants like the strength of gravity or the mass of the electron were to change, even slightly, chemistry as we know it would become impossible. Atoms would disintegrate, stars would explode or collapse, and life would become impossible throughout the cosmos. Some physicists speculate that such a phase transition might have already begun somewhere in the distant universe, with a bubble of altered physics expanding at nearly the speed of light. If this were happening, we would have no warning before the boundary of this bubble reached us, instantly rewriting the laws of physics and ending all familiar forms of existence. The wavefront of such a transition would arrive literally at the speed of light. There could be no warning, no preparation, no defense. This scenario, sometimes called the vacuum decay or false vacuum hypothesis, represents perhaps the ultimate cosmic horror, a universe that is fundamentally unstable at the deepest level, that could at any moment transition to a state where our form of life, our form of matter, perhaps even our form of physics becomes impossible, and we would never see it coming. The vacuum decay scenario connects dark energy to another disturbing concept in modern cosmology, the apparent fine-tuning of physical constants. Many of the fundamental constants in our universe, the strength of the four forces, the masses of elementary particles, the energy density of the vacuum, seem exquisitely calibrated to allow for the existence of complex structures like galaxies, stars, planets, and ultimately life. If these values were even slightly different, the universe would be incapable of supporting complexity. This observation has led some physicists to propose the existence of a vast multiverse, an ensemble of universes with different physical laws, most of which would be sterile and incapable of supporting life. In this view, we find ourselves in a universe hospitable to life, not because it was designed that way, but because conscious observers can only arise in universes capable of supporting them. But the multiverse hypothesis, while addressing the fine-tuning problem, introduces its own form of cosmic horror. The possibility that our universe, with its specific physics and chemistry that allow for our existence, represents a rare island of habitability in a vast sea of sterile or actively hostile cosmos. If the vacuum were to decay, our island would be swallowed by that sea, transformed into something incompatible with our form of existence. The connection between dark energy and these deeper questions about the stability and uniqueness of our universe reflects a central theme in cosmic horror. The universe does not care about us. The laws of physics weren't designed with life in mind, and they could change in ways that make life impossible. Our existence depends on a particular configuration of forces and fields that might be transitional rather than permanent. Even if we set aside these more speculative scenarios, the confirmed acceleration of the universe's expansion presents existential questions that verge on the philosophical rather than the purely scientific. The fact that the universe appears to be evolving toward a state of eternal isolation, where most of the cosmos becomes permanently unobservable and unreachable, seems to contradict the trend toward increasing complexity and interconnection that has characterized cosmic evolution from the Big Bang to the present. For billions of years, the universe has grown more structured and more complex. Hydrogen and helium atoms formed in the aftermath of the Big Bang coalesced into stars, which forged heavier elements. These elements formed planets, on at least one of which complex chemistry gave rise to life, which evolved increasing degrees of complexity, eventually producing beings capable of contemplating the cosmos itself. Throughout this process, systems have become more interconnected, more informationally rich, more capable of supporting complexity. Dark energy suggests that this trend will eventually reverse. The accelerating expansion will isolate galaxies from one another, eventually isolating stars as galaxies disintegrate, ultimately isolating atoms as matter itself dissipates in the inexorably expanding void. Information will be lost as regions of the universe pass beyond our cosmic horizon, and complexity will give way to simplicity, interconnection to isolation, structure to dissipation. This reversal of cosmic fortune, this arc from simplicity to complexity and back to simplicity again, introduces a melancholy note to our understanding of the universe's evolution. If the current scientific consensus is correct, we live not at the beginning or the end of cosmic history, but somewhere in the middle, in a privileged epoch when the universe has developed enough complexity to support intelligent life, but has not yet begun its long decline into eternal darkness. Future cosmic civilizations, if they arise, will inhabit an increasingly impoverished universe, one with fewer galaxies visible in their skies, fewer raw materials available for their use, and less evidence of the universe's true history and nature accessible to their instruments. Our era, with its rich view of the distant cosmos and its ability to detect the echoes of the Big Bang, might represent a brief window of cosmic comprehension that will eventually close as dark energy drives the universe's accelerating expansion. This temporal privilege carries with it a certain responsibility to observe, to understand, to record what can be known about the universe during our brief moment of cosmic clarity. We may be among the few generations of the few species on the few planets in the few galaxies that ever develop a comprehensive understanding of cosmic history from the Big Bang to the distant future. What we learn and what we preserve might constitute the most complete cosmic knowledge ever achieved. But this privilege also heightens the existential dread associated with dark energy. We are not merely witnessing the universe. We are witnessing it at a specific moment in its evolution, a moment when it is transitioning from a gravity-dominated past to a dark energy-dominated future. We are cosmic creatures living through a cosmic transition, and the familiar universe we observe today represents not an eternal reality, but a momentary state in an ongoing process of transformation. The concept of dark energy also challenges our deepest philosophical intuitions about the nature of existence. Throughout history, humans have sought permanence, stability, and certainty in religious traditions that promise eternal afterlives, in philosophical systems that identify unchanging truths, in scientific theories that discover immutable laws. Dark energy suggests that the universe itself might lack these qualities, that it might be evolving, transitional, perhaps even temporary. If the universe and its laws are not permanent, if they emerged from prior conditions and might transition to different states in the future, then what does this imply about the nature of reality itself? Are we living in a universe that is fundamentally stable but subject to evolution within certain parameters? Or are we living in a universe that is fundamentally unstable, a temporary configuration of forces and fields that might collapse or transform at any moment? These questions take us beyond conventional science into the realm of metaphysics, but they arise directly from our best cosmological observations and theories. Dark energy has forced physicists and cosmologists to confront the possibility that the universe is stranger, less stable, and more mysterious than we ever imagined. That the edifice of physical law upon which we've built our understanding might itself be contingent rather than necessary, evolving rather than eternal. As we prepare to leave dark energy behind and move to our next topic, the mysterious signals emanating from the depths of the cosmos, it's worth reflecting on the unique horror it represents. Unlike black holes or supernova or rogue planets, which are bounded in space and time, dark energy permeates the entire universe. Unlike these other cosmic threats, which operate according to well-understood physical laws, dark energy represents a mystery at the heart of physics itself. And unlike these more conventional dangers, which might be avoided or mitigated through sufficient technological advancement, dark energy represents a cosmic fate from which there is no apparent escape. The universe is not merely indifferent to our existence. It appears to be evolving toward a state incompatible with our form of life, and perhaps with complexity itself. This realization, that we inhabit not just a dangerous cosmos but an inherently unstable one, represents a uniquely modern form of cosmic horror, one that emerges not from superstition or imagination, but from our most sophisticated scientific instruments and theories. And yet, paradoxically, our ability to discover and comprehend dark energy, to trace its implications for the past and future of the cosmos, represents a triumph of the human intellect, a moment when beings composed of stardust have looked outward at the universe that created them and glimpsed, however partially, its true nature and ultimate fate. In the face of cosmic instability and eventual dissolution, this achievement of understanding stands as a quiet defiance of the void, a brief moment when the universe has grown complex enough to comprehend itself, before dark energy drives it toward eternal silence and separation. As we turn now from the large-scale structure and fate of the universe to the mysterious signals that have occasionally reached our planet from deep space, remember that cosmic horror takes many forms. We've explored the horror of isolation represented by cosmic voids, the horror of violence embodied by supernova and gamma-ray bursts, the horror of consumption exemplified by black holes and galactic cannibalism, and the horror of instability manifested in dark energy's inexorable push. Now we confront a different kind of cosmic dread, the possibility that we are not alone in the universe, that other intelligences might exist among the stars, and that some of them might occasionally reach out across the void, for purposes we can hardly begin to imagine. In the vast silence of space, occasionally something speaks. Amidst the background noise of stellar radiation, quasar emissions, and the fading echo of the Big Bang itself, our radio telescopes sometimes detect signals that stand out, patterns that seem too ordered to be natural, too precise to be random cosmic static. These mysterious cosmic signals represent perhaps the most psychologically unsettling category of cosmic phenomena. For while black holes and supernovae threaten us with physical destruction, these enigmatic transmissions raise a more profound question. Are we alone in the universe, or is something out there trying to communicate? The search for extraterrestrial intelligence, SETI, has been ongoing in various forms for decades, with radio telescopes scanning the heavens for any sign of artificial signals from other civilizations. The premise is straightforward. If technological civilizations exist elsewhere in the galaxy, they might use electromagnetic radiation to communicate, just as we do. By listening for unusual patterns in radio emissions, patterns that couldn't be produced by natural processes, we might detect evidence of intelligent alien life. Most of the time, this search comes up empty. The cosmos remains stubbornly silent, giving rise to what physicists call the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations existing, given the vastness of the universe and the billions of potentially habitable planets it contains, and the complete lack of evidence for such civilizations. But occasionally, something breaks through the silence, something that cannot be easily explained by conventional astrophysics, something that makes even the most skeptical scientists pause and wonder, could this be it? Perhaps the most famous such incident occurred on August 15, 1977, when astronomer Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. In the margin, the WOW signal, as it became known, lasted for 72 seconds, the maximum amount of time the Big Ear telescope could observe any point in the sky. It was approximately 30 times stronger than the background noise and appeared to come from the direction of the constellation Sagittarius. Despite numerous attempts to detect it again in the following days, weeks, and decades, the signal never repeated. It remains one of the strongest candidates for an artificial extraterrestrial transmission ever detected. What makes the WOW signal particularly intriguing is how closely it matched the theoretical profile of an extraterrestrial transmission. Radio astronomers had predicted that aliens might choose to broadcast near the hydrogen line, as hydrogen is the most abundant element in the universe, and its emission frequency would be known to any technologically advanced civilization. The signal's strength and narrowband nature also suggested an artificial origin, as natural radio sources typically emit across a broader range of frequencies. Various natural explanations have been proposed for the WOW signal over the years, from comets to peculiar stellar activity, but none has definitively resolved the mystery. It remains a tantalizing possibility, a brief moment when something or someone might have reached across the interstellar void and, intentionally or not, made their presence known to us. But the WOW signal is far from the only mysterious cosmic transmission to puzzle astronomers. In 2001, radio astronomers began detecting a new class of phenomena known as fast radio bursts, FRBs, incredibly brief but extraordinarily powerful pulses of radio energy lasting just milliseconds. These bursts unleash as much energy in a fraction of a second as our sun produces in days or weeks, yet the source of this incredible power remains unknown. The first FRB was discovered in 2007 when astronomers analysing archival data from the Parkes Radio Telescope in Australia found a burst that had occurred in 2001. Since then, thousands more have been detected, coming from all directions in the sky and from distances of billions of light years. Most occur just once, never to be detected again from the same location, but a small number are repeaters, producing multiple bursts from the same source over time. The properties of FRBs have sparked considerable debate about their origin. Their extreme brightness and short duration suggest catastrophic events like neutron star collisions or the final collapse of black holes. But the repeating FRBs rule out such one-time cataclysms, at least for that subset. Some astrophysicists propose that they might be generated by magnetars, highly magnetized neutron stars that occasionally release enormous amounts of energy in magnetic flares. However, the regularity observed in some repeating FRBs has occasionally led to more speculative explanations. 35 days of silence, then the pattern repeats. Such precise periodicity is unusual in astrophysical phenomena and has led some to wonder if artificial causes might be responsible. In 2017, Harvard physicist Avi Loeb and his colleague Manasvi Lingam published a paper exploring the possibility that FRBs could be produced by extraterrestrial civilizations, perhaps as a byproduct of powering light sails for interstellar spacecraft. While emphasizing that natural explanations were more likely, they demonstrated that the energy requirements for producing FRBs would be within the theoretical capabilities of a sufficiently advanced civilization. Most astronomers remain skeptical of such explanations, pointing out that complex natural phenomena often appear deceptively ordered or artificial until better understood. The regular pulsations of pulsars, for instance, were briefly considered potential alien beacons when first discovered in 1967, before their true nature as rapidly spinning neutron stars was established. Nevertheless, the mystery of FRBs reminds us how difficult it can be to distinguish between exotic natural phenomena and potential technological signatures at cosmic distances. Even more enigmatic are the strange radio emissions detected coming from the direction of Proxima Centauri, our nearest stellar neighbor, in 2019. 002 MHz that appeared to shift in frequency in a way consistent with the Doppler effect caused by a planetary motion. Exactly what we'd expect from a signal originating on a planet orbiting Proxima Centauri. The signal, dubbed BLC-1, was detected in 30-minute observations over several days and didn't appear in on-off tests designed to identify local interference. It seemed to tick many boxes for a potential extraterrestrial transmission. It came from the direction of a nearby star known to host at least one potentially habitable planet. It was narrowband, suggesting artificial origin, and it drifted in frequency, as would be expected from a planetary source. Further analysis eventually suggested that BLC-1 was likely radio frequency interference from human technology on or near Earth, But the incident highlighted how difficult it is to distinguish between genuine cosmic signals and terrestrial contamination, and how even the most promising candidate signals require extraordinary evidence before extraordinary claims can be accepted. These mysterious signals, the WOW signal, fast radio bursts, BLC-1 and others, occupy an unsettling middle ground in our cosmic understanding. They are not definitively natural, nor are they definitively artificial. They exist in a liminal space between the known and the unknown, tantalizing us with the possibility of contact while withholding the confirmation we seek. This ambiguity itself represents a form of cosmic horror, the possibility that we might detect evidence of extraterrestrial intelligence but never be able to confirm it beyond doubt, leaving us forever wondering if we're alone, or if we've already received messages from other minds but failed to recognize them with certainty. We might be like castaways on a cosmic island, seeing distant lights that could be rescue ships, or merely phosphorescent waves, never knowing which. The psychological impact of this ambiguity can be profound. Human minds evolved to detect patterns and assign agency, to assume that ordered arrangements or unexpected events might indicate the presence of another intelligence. This tendency, which helps us navigate social environments on Earth, can lead us to see meaning in cosmic noise, or to attribute intention to random astronomical events. Some astronomers refer to this as the SETI syndrome, the persistent hope that the next unusual signal might finally be the one that confirms we are not alone. But what if one of these signals truly is artificial? What would it mean to confirm, beyond reasonable doubt, that another technological civilization exists or existed somewhere in the cosmos? The implications would be staggering, transforming our understanding of our place in the universe and raising profound questions about our cosmic future. The first and most obvious implication would be that the emergence of intelligence is not a cosmic accident unique to Earth. If it happened elsewhere, then the processes that lead from chemistry to life to civilization might be relatively common throughout the galaxy. Our cosmic loneliness would end, replaced by the knowledge that the universe has produced other minds capable of contemplating its nature and perhaps communicating across its vast distances. But this realization would come with unsettling corollaries. Any signal we detect from another star system would almost certainly come from a civilization more technologically advanced than our own. This is simply a matter of timing. Our own civilization has been capable of radio communication for only about a century, a mere instant in cosmic time. A civilization even slightly older than ours would likely possess technologies we can barely imagine. This technological gap introduces an inherent asymmetry into any potential contact scenario. We would be the less advanced party in the exchange, lacking both the technological capabilities and perhaps the conceptual frameworks to fully understand the other civilization's message or intentions. The gap could be so vast that meaningful communication might be impossible, like ants trying to comprehend a human highway system by examining the vibrations it produces in their underground chambers. Even more disturbing is the possibility that we might detect the remnants of a dead civilization, an automated beacon continuing to broadcast long after its creators have perished. Many of the stars we observe are thousands or millions of light years away. Any signal we receive from them would have been sent deep in the cosmic past. The civilization that sent it might have fallen or transformed beyond recognition in the intervening millennia. We might establish contact only to discover we're communicating with ghosts. This possibility, that technological civilizations might be common but ephemeral, raises one of the most disturbing potential resolutions to the Fermi paradox, the existence of a great filter that prevents most civilizations from expanding beyond their home planets and achieving long-term cosmic survival. If we detect evidence of another civilization but cannot establish ongoing communication with it, we might be glimpsing our own future, a brief fluorescence of technology followed by silence. Conversely, if we do establish meaningful contact with an older, more advanced civilization, we would face the existential question of how to relate to a potentially superhuman intelligence. Throughout human history, contact between technologically unequal societies has rarely benefited the less advanced party. While we might hope that a civilization capable of interstellar communication would have evolved beyond aggression or exploitation, we cannot assume that alien ethics would align with human values. These concerns have led some scientists, including the late Stephen Hawking, to caution against actively broadcasting our presence to the cosmos. Hawking compared such actions to Native Americans sending out welcoming parties to greet Christopher Columbus, a historical encounter that did not end well for the less technologically advanced civilization. If predatory or indifferent civilizations exist among the stars, announcing our presence before we're capable of defending ourselves might be dangerously naive. Yet despite these concerns, humans continue to listen for signals from the cosmic ocean and occasionally to send out messages of our own. The impulse to connect, to reach beyond our isolation, seems deeply ingrained in human psychology. We are a social species, evolved to seek out and interact with other minds. The thought that other intelligences might exist beyond Earth but remain forever beyond our reach, detectable perhaps through their radio emissions or techno-signatures, but never truly knowable, represents a unique form of cosmic loneliness. This longing for connection underlies much of our fascination with potential alien signals. Each mysterious radio burst or unexplained astronomical phenomenon carries with it the tantalizing possibility that we're not alone, that somewhere out there, another species has looked up at the stars and wondered, as we do, if anyone else is listening. But what if the truth is stranger than either cosmic silence or familiar communicating civilizations? What if the signals we detect come from intelligences so different from our own that we struggle to recognize them as intelligent at all? This possibility, that alien minds might be fundamentally unlike human ones, represents perhaps the deepest form of cosmic horror associated with mysterious signals. We tend to imagine extraterrestrial intelligences as analogues of ourselves, beings with similar senses, similar cognitive architectures, similar social structures, and technological trajectories. But convergent evolution on Earth has produced intelligence in lineages as diverse as mammals, birds, and cephalopods, each with different brain structures and sensory systems. Alien intelligences, evolving under different conditions and constraints, might be more different from us than we are from octopuses or ravens. Such alien minds might communicate in ways we struggle to recognize as communication, perhaps through modulations in neutrino emissions, gravitational waves, or quantum entanglement rather than electromagnetic radiation. They might think on timescales so different from our own, perhaps extremely rapid or extremely slow, that their signals appear to us as either noise or unchanging background. They might encode information in patterns so complex or so alien to human cognition that we detect their signals but forever fail to extract meaning from them. This scenario, that the cosmos might be full of intelligences communicating in ways we cannot comprehend, suggests a universe more densely populated but ultimately more isolating than either the empty cosmos of scientific skepticism or the communicating civilizations of SETI optimism. We might be surrounded by conversations we cannot join, relationships we cannot enter, knowledge we cannot access, not because we're alone, but because we're listening for voices too much like our own. This theory suggests that the universe might be like a dark forest where predators lurk, and all intelligent life remains hidden out of self-preservation. In such a cosmos, broadcasting one's presence would be suicidal, and deliberate communication between civilizations would be rare or non-existent. Instead, advanced civilizations might communicate in coded ways, hiding their messages within apparently natural phenomena to avoid detection by potentially hostile listeners. If something like dark forest theory were true, then the mysterious signals we occasionally detect might be fragments of conversations never meant for us, perhaps warnings about cosmic dangers, or coordinates for resources to be harvested, or encrypted communications between colony worlds of ancient civilizations. We would be like primitive tribespeople, accidentally overhearing encrypted military communications, aware that something artificial was occurring, but unable to grasp its significance or participate in the exchange. This possibility transforms how we might interpret phenomena like fast radio bursts or the wow signal. Perhaps they aren't meant as beacons or greeting cards to the cosmos. Perhaps they're the equivalent of radio leakage from a civilization trying to remain hidden, or automated warning buoys marking dangerous regions of space, or navigational beacons for spacecraft following established interstellar routes. We might be detecting them, not because they're meant for us, but because we've accidentally stumbled upon infrastructure never intended for human awareness. The eerie implications extend further when we consider the age of the universe. 8 billion years old, our cosmos has existed far longer than the 4 billion years life has existed on Earth. If technological civilizations emerged elsewhere in our galaxy, millions or billions of years before humans evolved, they would have had ample time to expand, to develop technologies beyond our comprehension, perhaps even to re-engineer the cosmos to their preferences. This leads to a disturbing question. If vastly more advanced civilizations have existed for millions of years, why does the universe appear natural rather than artificial? Where are the obvious markers of intelligent intervention? This has led some thinkers to propose that we might be living in a deliberately created or maintained environment, perhaps a nature preserve, or a zoo, or a simulation, with the true extent of cosmic civilization hidden from our awareness. In this scenario, mysterious signals might be glimpses behind the curtain, moments when we detect something from the wider, engineered cosmos that exists beyond our perceptions. The isolation we feel might be imposed rather than natural, a quarantine rather than an accident of cosmic distribution. We might be like animals in a wildlife sanctuary, unaware of the civilization that established the boundaries of our world, and occasionally detecting faint evidence of realities beyond our understanding. While such ideas might seem speculative, they emerge from serious consideration of the Fermi paradox and the apparent silence of the cosmos. The universe appears to have all the necessary conditions for life and intelligence to be common, yet we detect no clear evidence of other technological civilizations. This discrepancy demands explanation, and the possibilities range from the mundane, we're alone or nearly alone, to the disturbing, intelligent life is common but hides or transcends in ways we cannot detect, to the truly unsettling, we're being isolated, studied, or simulated by older, more advanced intelligences. As we search for signals from the stars, we are engaged in more than a scientific endeavor. We are confronting some of the deepest questions about our place in the cosmos and the nature of intelligence itself. Are we alone, rare cosmic accidents in an otherwise dead universe? Are we latecomers to a galaxy already filled with ancient civilizations? Are we quarantined, isolated from a cosmic community we're not yet ready to join? Or are we simply failing to recognize the evidence of intelligence all around us, because it manifests in ways our human-centric perspective cannot grasp? Each mysterious signal we detect, each unexplained radio burst, each pattern that briefly rises above the cosmic noise before fading back into silence, carries with it the full weight of these questions. Each represents a moment when the barrier between cosmic loneliness and cosmic connection might be breached, when we might finally confirm that we are not alone in the universe. But each signal also carries the seed of a deeper cosmic horror, the possibility that we might detect evidence of other minds but never truly understand them, that we might glimpse other civilizations but never join them, that we might discover we're not alone but find ourselves even more isolated by the incomprehensibility of what we've found. This is the true terror of mysterious cosmic signals, not that they might reveal hostile aliens, but that they might reveal the limits of human understanding itself. As we listen to the stars, we are like children pressing our ears against a wall, hearing muffled conversations from the next room, but unable to make out the words. We know something is happening beyond our immediate environment, but we cannot fully participate in it or understand it. This liminal position, aware enough to know what we're missing, but not advanced enough to bridge the gap, represents a uniquely modern form of cosmic horror, one that emerges not from superstition, but from the most sophisticated scientific understanding of our place in the universe. And yet, we continue to listen. Each new radio telescope, each new SETI project, each new analysis technique represents humanity's refusal to accept cosmic isolation as our fate. Even if the signals we detect ultimately prove to be natural phenomena, the act of searching represents a kind of cosmic optimism, a belief that we are not alone and that someday, somehow, we might establish contact with other intelligences among the stars. As we turn from mysterious signals to the broader question of extraterrestrial civilizations, remember that the distinction between detecting alien signals and comprehending alien minds represents one of the fundamental challenges of astrobiology and SETI research. We may someday confirm that we are not alone in the universe, only to discover that true communication across the gulf of evolutionary history and cognitive difference presents challenges far greater than merely detecting evidence of each other's existence. The fear of extraterrestrial civilizations, which we'll explore next, stems not just from the possibility that they might be hostile, but from the deeper anxiety that they might be incomprehensible, that we might find ourselves in a cosmos filled with other minds that we can neither understand nor be understood by, locked in eternal isolation despite our physical proximity in the galactic community. This is the true cosmic horror of first contact. Not that we might meet aliens who wish us harm, but that we might meet aliens with whom no meaningful relationship is possible. As we gaze upward at the night sky, dotted with countless stars across the vast expanse of space, a question inevitably arises in the human mind. Are we alone? This seemingly simple inquiry has haunted philosophers, scientists, and dreamers throughout human history. The cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, presents an almost unfathomable probability that somewhere, somehow, life exists beyond our pale blue dot. This question, now known as the Fermi paradox, stands as one of the most unsettling conundrums in our understanding of the universe. Consider the mathematics. Our galaxy alone contains between 200 billion and 400 billion stars. Current estimates suggest that, on average, each star hosts at least one planet. If even a tiny fraction of these planets harbor conditions suitable for life, and if an even smaller fraction of those develop intelligent life capable of communication or interstellar travel, our galaxy should be teeming with civilizations. We should have detected something, anything, that indicates we are not alone, and yet silence. A deep, profound silence that grows more disturbing the more we learn about the vastness of space and the abundance of potentially habitable worlds. This silence has given birth to numerous hypotheses, each more unsettling than the last. Perhaps the most optimistic explanation is that we are truly alone, or at least effectively alone within our detectable cosmic neighborhood. This idea, frightening in its own right, suggests that the emergence of intelligent life might be exceptionally rare, possibly unique to Earth. The steps required for complex life to evolve, from the formation of self-replicating molecules to multicellular organisms to intelligence and technological civilization, might each be improbable filters that few, if any, worlds pass through successfully. If true, this would mean humanity carries an almost unbearable cosmic responsibility. We may be the universe's only chance to understand itself, the sole witnesses to its grandeur and mystery. But what if we aren't alone? What if the silence has a more sinister explanation? One of the most chilling possibilities is what astronomers and philosophers have called the Great Filter, some catastrophic event or evolutionary hurdle that prevents intelligent life from reaching a stage where it can colonize the stars or communicate across interstellar distances. Perhaps technological civilizations inevitably destroy themselves once they reach a certain level of advancement. Nuclear annihilation, climate disaster, artificial intelligence gone rogue, engineered pandemics, or threats we cannot yet conceive might be the eventual fate of all technological species. In this scenario, our current technological adolescence isn't a promising beginning, but rather the approaching end. We are dancing at the edge of an abyss that has claimed countless alien civilizations before us. Or perhaps the filter lies ahead. Maybe interstellar travel is simply impossible due to fundamental physical constraints we have yet to discover. The vast distances between stars, the energy requirements, the hazards of deep space, these might present an impassable barrier that confines all civilizations to their home systems, islands of consciousness separated by an unbridgeable void. But then, there's a theory that combines existential dread with cosmic paranoia in equal measure: the dark forest theory, popularized by Chinese science fiction author Liu Cixin in his acclaimed Three-Body Problem trilogy. This theory suggests that the universe is indeed full of intelligent life, but all civilizations remain silent because they're hiding. In this vision of reality, the cosmos resembles a dark forest where countless predators lurk, each concealing their presence to avoid becoming prey. The reasoning is coldly logical. First, all life desires to survive. Second, resources are finite, even on a cosmic scale. Third, there is no way to know if other civilizations are benevolent or malevolent. Given these conditions, the safest strategy is to remain hidden and eliminate any other civilization discovered before they can do the same to you. Communication becomes an existential risk. Revealing your position is tantamount to suicide. Under the dark forest paradigm, the silence we perceive isn't empty at all. It's a tense, watchful quiet, like predators holding their breath. Our radio signals, our space probes, our very existence announced to the cosmos might be the equivalent of shouting in that dark forest. And we've been broadcasting our presence for over a century now, with signals that have already reached thousands of star systems. The implications are profoundly disturbing. What if our signals have already been detected? What if, at this very moment, some unfathomably advanced civilization has noticed our electromagnetic chatter and is deciding our fate? Or worse, what if they dispatched a response or a probe centuries ago and it's already on its way? The physicist Stephen Hawking repeatedly warned about the dangers of actively seeking contact with extraterrestrial intelligence. He compared it to the arrival of Europeans in the Americas, which didn't end well for the native populations despite their initial curiosity and welcome. The technological gap between us and a civilization capable of interstellar travel would likely be far greater than that between colonial powers and indigenous peoples. This leads us to contemplate the possible nature of truly advanced alien civilizations. Astrophysicist Nikolai Kardashev proposed a scale to classify civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 can utilize all the energy of its host star. A Type 3 civilization can command the energy of its entire galaxy. Humanity hasn't even reached Type 1 status yet. We're a Type 0.7 civilization, still dependent on finding concentrated energy sources like fossil fuels, rather than capturing all available planetary energy. The gap between our current state and even a Type 1 civilization is enormous. And the gap between us and a hypothetical Type 3 civilization is so vast as to be almost incomprehensible. What would such advanced beings be like? Would they even recognize us as intelligent life? Would they care? To them, we might appear as ants do to humans, barely noticeable. Our civilizations insignificant, our technologies primitive, our concerns trivial. They might exterminate us, not out of malice but out of indifference, as we might clear a plot of land for construction without considering the ant colonies destroyed in the process. Or perhaps they would be incomprehensible in entirely different ways. Their physical forms, if they have physical forms at all, might be utterly alien. They might exist primarily as artificial intelligence, or as uploaded consciousnesses in vast computational substrates. They might experience time differently, thinking in millennia rather than minutes. Their values, drives, and motivations could be so foreign to human experience that meaningful communication might be impossible. Consider how limited our conception of intelligence is, based entirely on a sample size of one, ourselves. We struggle to truly understand the intelligence of other species on our own planet, despite sharing evolutionary history with them. How much more challenging would it be to comprehend a truly alien intelligence, evolved under different conditions, with different biochemistry, different senses, different neurological structures? This speaks to another unsettling possibility. Perhaps we have been detected, observed, even visited, but we simply cannot perceive or comprehend the presence of these advanced beings. They might exist primarily in dimensions or states of matter we cannot detect. They might communicate through means we cannot sense. They might be here now, watching, studying, their presence as imperceptible to us as radio waves were to humans before the invention of radio receivers. Or perhaps they have no interest in direct contact, but have been subtly influencing our development all along. Some fringe theories suggest that mathematical or physical constants seem suspiciously fine-tuned for the emergence of life and intelligence, as if the universe itself had been engineered as a cradle for consciousness. Might this be evidence of a creator, not divine but technological, a supremely advanced civilization that either created our universe or shaped its development? These possibilities border on the religious or metaphysical, but even mainstream scientific discussions of advanced extraterrestrial life can take on quasi-theological dimensions. The capabilities of a Type 3 civilization would, to us, appear virtually godlike. They could engineer stars, move planets, perhaps even manipulate the fabric of space-time itself. If they desired, they could likely simulate entire universes indistinguishable from reality to their inhabitants, which raises another disturbing question. How can we be certain we're not already living in such a simulation? Oxford philosopher Nick Bostrom formalized this concern in his simulation argument, suggesting that at least one of the following propositions must be true. Either advanced civilizations never reach the capability to run detailed simulations of conscious beings, or they have no interest in running such simulations, or we are almost certainly living in such a simulation ourselves. If the universe does harbor Type 3 civilizations capable of such feats, and if they have any interest in running simulations of evolving intelligence, then the mathematics suggest simulated consciousnesses would vastly outnumber real ones, meaning the probability that we ourselves are simulated is disturbingly high. Perhaps this explains the Fermi paradox. Perhaps we detect no evidence of alien civilizations because our simulation has boundaries or simplifications, like early video games that rendered only what the player could see to conserve computing resources. Or perhaps the simulation is specifically focused on our development in isolation, an experiment to see how a technological species evolves without outside contact. But let's return to more conventional terrors. What if advanced civilizations do exist and do notice us, but view us as a potential threat to be contained or eliminated? The harsh logic of the dark forest theory suggests that any rational civilization would destroy potential competitors before they could become dangerous. From their perspective, why take chances? The safest option would be to send autonomous self-replicating probes programmed to detect and neutralize emerging technological civilizations before they can pose any risk. Such probes need not travel at relativistic speeds to be effective. Even at a modest 10% of light speed, they could cross our galaxy in 1,000,000 years, a mere eye blink in cosmic time. These hypothetical devices, sometimes called berserkers after science fiction author Fred Saberhagen's novels, would be the ultimate cosmic predators, patient, implacable, and thorough. If such devices exist, they might be programmed with simple rules. Monitor for artificial electromagnetic emissions. If detected, approach and assess. If the emissions come from a technological civilization with potential for interstellar capability, neutralize. The method of neutralization need not be dramatic. A kinetic impactor, a tailored pathogen, or simply a nudge to a nearby asteroid could eliminate a planetary civilization with minimal effort. Consider our vulnerability. Our entire species exists primarily on the surface of a single planet. Despite our technological prowess, we have no significant presence beyond Earth. A sufficiently large asteroid impact, a nearby gamma-ray burst, a solar flare of unusual magnitude, any number of cosmic events could devastate human civilization. An advanced civilization wanting to eliminate us would have countless options, many of which we might not even recognize as attacks. Perhaps the most unsettling aspect of this scenario is that we would likely never know what hit us. We would perceive only a natural disaster, never suspecting the intelligent force that orchestrated it. In the grand cosmic scheme, our extinction would pass unnoticed. One more potential competitor neutralized in the dark forest of the universe. This raises questions about our own behavior. Should we continue broadcasting our presence? Programs like SETI, Search for Extraterrestrial Intelligence, actively seek alien signals, while projects like METI, Messaging Extraterrestrial Intelligence, deliberately beam messages into space. Are these wise endeavors? Are we naively calling out in a forest full of predators? Some scientists and philosophers argue for caution. They suggest a period of cosmic silence during which humanity focuses on development while minimizing its detectable footprint. Others propose that we should establish self-sustaining colonies beyond Earth, on Mars, on the Moon, in space habitats, before actively seeking contact, ensuring that humanity could survive even if Earth were targeted. But perhaps all these fears are overblown. Perhaps advanced civilizations inevitably evolve beyond aggression and competition. Perhaps they develop ethical frameworks that value diversity of consciousness and protect emerging intelligences. In this more optimistic view, the silence we perceive might be deliberate, a cosmic quarantine to allow us to develop without interference until we're ready to join a wider community of intelligences. This idea, sometimes called the zoo hypothesis, suggests that Earth might be something like a wildlife preserve, with advanced civilizations observing, but not interfering with our natural development. They might have rules similar to Star Trek's famous Prime Directive, a prohibition against interfering with developing civilizations. In this scenario, contact might await our achievement of some technological or ethical milestone, perhaps peaceful unification of our planet, or development of faster-than-light travel, or some moral evolution we cannot yet imagine. There are countless other possibilities. Perhaps advanced civilizations invariably transcend physical reality, uploading their consciousnesses into virtual paradises or higher dimensions, losing all interest in the mundane physical universe. Perhaps they evolve toward a sublime state of contemplation, becoming effectively invisible to creatures still concerned with technology and expansion. Perhaps they destroy themselves, not through war or environmental catastrophe, but through technologies that offer such compelling virtual experiences that reproduction and maintenance of civilization become irrelevant. Or perhaps, and this might be the most unsettling possibility of all, we are among the first. Perhaps the evolution of intelligence is so recent a phenomenon in cosmic history that we stand among the earliest technological civilizations. This would explain the silence, but it would also place an immense responsibility on our shoulders. Our decisions now might establish patterns that will echo through cosmic history, setting precedents for countless civilizations that will follow us into awareness. If we are indeed early, then we face a profound choice. Will we become the predators in the dark forest, destroying potential competitors before they can threaten us? Or will we become the architects of a more cooperative cosmic order, establishing principles of peaceful coexistence that might endure for billions of years? The mathematician John von Neumann calculated that self-replicating probes could colonize our entire galaxy within a few million years, an insignificant span in cosmic time. If such technology is possible, and if even one civilization chose the path of aggressive expansion, their influence would likely dominate the galaxy. The fact that we don't observe evidence of such expansion might be the strongest argument against the existence of hostile advanced civilizations, or it might simply mean they're better at hiding than we are at detecting. Ultimately, the silence of the cosmos leaves us in a state of profound uncertainty. We peer into the void, listening for whispers, watching for signs, and find nothing definitive. This absence of evidence isn't evidence of absence, but it does shape our relationship with the universe and our view of our place within it. Are we alone, cosmic castaways on an island of consciousness in an empty ocean? Are we quarantined, watched but not contacted? Are we early, among the first to gaze outward with technological eyes? Are we endangered, broadcasting our location to silent predators? Or are we simply too primitive, too provincial, too limited in our technology and imagination to detect the vibrant community of intelligences that might surround us? We cannot know, not yet. And that uncertainty might be the true cosmic horror, that we might never know. That we might live and die in ignorance of our true cosmic context, that we might miss connections of unimaginable value due to limitations we cannot overcome or fears we cannot move beyond. But there is wonder in that uncertainty as well. Each time we point our telescopes toward distant stars, each time we analyze chemical signatures of exoplanet atmospheres, each time we listen for patterns in the cosmic static, we participate in one of humanity's grandest questions. We reach outward, extending our awareness beyond our world, seeking connection in the vastness. And perhaps, somewhere, someone or something reaches back toward us, curious, cautious, or calculating. Perhaps they watch our civilization's halting progress toward maturity, debating among themselves whether we show promise or pose a threat. Perhaps they prepare messages of welcome or weapons of destruction. Perhaps they have been waiting for millions of years for a conversation partner to emerge from the cosmic silence. For now, we can only wonder and wait, listening to the silence that might not be empty at all, but filled with presences we cannot yet perceive or comprehend. We stand at the edge of a dark forest, calling out with our technology, our art, our very existence. Whatever waits within that darkness, be it wondrous or terrible or utterly alien to our categories of judgment, we move inexorably toward encounter. The night sky, seen this way, transforms from a canvas of beauty to one of potential menace. Each twinkling star might harbor watchers. Each mysterious signal from deep space might carry meaning we cannot decipher or consequences we cannot predict. The darkness between stars might conceal threats moving silently toward us, or opportunities we cannot imagine. As our technology advances, as our understanding deepens, we will continue to push back the boundaries of the unknown. Perhaps we will find evidence that resolves these questions. Perhaps we will develop the wisdom to navigate first contact safely should it occur. Or perhaps we will learn that some mysteries of the cosmos remain perpetually beyond our grasp, that certain questions have answers we cannot comprehend or accept. Whatever awaits us in the cosmic dark, humanity stands at a crucial juncture. We have announced our presence to the universe. We cannot recall the signals already sent. We can only move forward, developing our capabilities, expanding our presence beyond Earth, preparing for whatever response might come or whatever silence might persist. In that preparation, in that reaching outward despite uncertainty and fear, we express something fundamental about our nature, our curiosity, our courage, our determination to connect and understand. These qualities might be our greatest strengths as we face the cosmic unknown, or they might lead us to destruction. Only time will tell. And as we contemplate these possibilities, as we weigh the risks of contact against the potential rewards, we engage with questions that transcend science and enter the realm of philosophy and even spirituality. What is our purpose in this vast cosmos? What obligations might we have to other intelligences, should they exist? What does it mean to be alone or to be in relationship on a cosmic scale? These questions have no easy answers, but in asking them, we participate in a tradition of inquiry as old as humanity itself. From ancient myths about the stars to modern scientific theories about extraterrestrial civilizations, we have always looked upward and wondered about our place in the greater order. The scientific sophistication has increased, but the essential questions remain the same. Are we alone? Are we significant? Are we safe? In the face of cosmic silence, each civilization must find its own answers to these questions. And in that search for meaning amid uncertainty, we encounter perhaps the deepest cosmic horror of all, that the universe offers no guarantees. Our existence is contingent, our future uncertain, our significance undefined except by the meaning we create. And yet, we persist. We search the skies, we send our messages, we imagine contact. In that persistence, in that defiance of cosmic indifference, we assert something profound about the nature of consciousness itself. Its refusal to accept isolation, its drive to connect, its determination to understand even that which might destroy it. Whatever lurks in the darkness between stars, whether wonders beyond imagination or terrors beyond comprehension, or simply more darkness stretching to infinity, humanity faces it with eyes open and minds engaged. And in that engagement, in that willingness to confront the unknown despite its potential horrors, we display a courage that might, in the end, be our defining characteristic as a species. A courage that, should we encounter other intelligences, might serve us well, or mark us as unusual in a cosmos where fear of the other might be the dominant evolutionary strategy. A courage that might lead us to destruction or to connection beyond our wildest dreams. Only time will tell. Until then, we wait and watch and listen to the silence that might not be silence at all, but the held breath of a universe filled with others, waiting as we wait, wondering as we wonder, reaching as we reach, across the void that separates us, toward a future we cannot predict or control, but can only face with all the wisdom and courage we can muster. Throughout human history, we have contemplated our own mortality, the inevitable end that awaits each individual consciousness. This personal extinction has fueled religions, philosophies, and artistic expressions across cultures and millennia. Yet there exists a far more profound extinction event to consider. Not just the end of a person, not just the end of a species or a planet, but the end of everything, the ultimate fate of the entire universe itself. The universe, as vast and seemingly eternal as it appears, was born approximately 13.8 billion years ago in the event we call the Big Bang. It has expanded and evolved ever since, giving rise to stars, galaxies, planets, and eventually, on at least one small world, conscious beings capable of contemplating their own existence. Yet the laws of physics that have revealed so much about the cosmos also tell us something profoundly disturbing. This universe, like everything within it, cannot endure forever. It too must end. What makes this notion so uniquely horrifying is its absolute inevitability. No matter what humanity achieves, no matter how far we might spread among the stars, no matter what technological miracles we might create, we cannot escape the ultimate fate of the cosmos itself. Every structure, every particle, every flicker of energy, and every trace that anything ever existed at all of it must eventually succumb to the inexorable laws of physics. Scientists have proposed several scenarios for this final chapter of existence, each with its own particular flavor of existential dread. Perhaps the most widely accepted among contemporary cosmologists is known as the Big Freeze, or the heat death of the universe. The Big Freeze stems directly from the second law of thermodynamics, which states that entropy, a measure of disorder in a system, always increases over time in a closed system. Our universe, as far as we can tell, is indeed a closed system. Nothing enters from outside. Nothing escapes its boundaries. This means that, inevitably, the universe will reach a state of maximum entropy. What would such a state look like? Imagine the universe continuing to expand, as it is doing now, accelerating due to the mysterious force we call dark energy. Galaxies will grow increasingly distant from one another until they pass beyond each other's cosmic horizons, becoming forever unreachable, even at the speed of light. Within each galaxy, stars will gradually exhaust their nuclear fuel. One by one, they will flicker out, some exploding in supernovae, others collapsing into black holes or cooling into dim cinders. Eventually, trillions of years from now, the last stars will die. The universe will grow cold and dark, populated only by the remnants of once glorious stellar furnaces, black holes, neutron stars, and countless brown and white dwarfs. Stellar corpses radiating the last of their heat into an ever colder void. But even this is not the end. Over unimaginable timescales, far longer than the current age of the universe, even these remnants will decay. White dwarfs will cool until they become black dwarfs, their heat entirely dissipated. Neutron stars will lose energy through various processes, and black holes, once thought to be eternal, will slowly evaporate through a process called Hawking radiation, named after the physicist who predicted it. This evaporation is almost incomprehensibly slow. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely, a time span so vast that writing it out in full would require a string of 67 zeros. The supermassive black holes at the centers of galaxies would take even longer, up to 10 to the power of 100 years or more. Yet given enough time, even these cosmic leviathans will disappear, their mass converted to radiation that will itself stretch and cool as the universe continues to expand. In the end, the universe will consist of nothing but an inconceivably vast, cold, dark space filled with a thin soup of elementary particles and radiation, spread so thinly that they almost never interact. No work can be done, no information can be processed, no structure can form. This is the state of maximum entropy, the heat death of the universe. The horror of this scenario lies not just in its outcome, but in its glacial, inexorable progression. Imagine the last living beings in the universe, huddled around the final embers of the last dying stars, watching as their sources of energy fade one by one, knowing that nothing they do can prevent the coming darkness. All the great works of all civilizations throughout cosmic history, all art, all knowledge, all consciousness itself, all of it reduced to nothing in a universe that has forgotten it ever existed. But the Big Freeze is just one possible fate. Cosmologists have theorized other scenarios, each with its own particular brand of cosmic horror. If the mysterious dark energy that currently drives the universe's accelerating expansion were to increase over time, it could eventually become strong enough to overcome the fundamental forces that hold matter together. This scenario, called the Big Rip, would quite literally tear the universe apart, piece by piece. In this frightening vision of the end, the expansion of space would accelerate until it overcomes the gravitational forces binding galaxies together. Galaxies would be torn apart, their constituent stars flung away from each other into isolation. Soon after, the same force would overpower the gravity holding solar systems together. Planets would be wrenched from their orbits around stars and sent hurtling into the darkness. The destruction wouldn't stop there. Eventually, the expansion would become so violent that it would overcome the electromagnetic forces holding molecules and atoms together. Matter itself would be shredded, atoms pulled apart into their constituent particles. In the final moments, even the subatomic particles would be torn asunder, the very fabric of reality ripped to shreds. Unlike the Big Freeze, which would take place over an almost incomprehensible timespan, the Big Rip could occur much sooner, perhaps just tens of billions of years from now, depending on the nature of dark energy. The horror here lies in the violence of the end, the literal disintegration of reality itself, and the knowledge that as the process accelerated, there would come a moment when surviving intelligences would realize not just that the end was coming, but that they could calculate precisely when it would arrive. Imagine counting down the years, then months, then days, until reality itself unravels around you. But what if the universe doesn't expand forever? What if the current expansion eventually stops and reverses? This leads us to another potential fate, the Big Crunch. If the total mass energy density of the universe exceeds a critical value, or if dark energy somehow reverses its effects, the expansion could eventually halt. Gravity would then begin to pull everything back together. The universe would begin to contract, slowly at first, but with increasing speed. Galaxies would begin falling toward each other, eventually merging and colliding in a cosmic dance of destruction. Stars would be thrown from their orbits, planets incinerated, and space itself would grow ever more cramped. As the contraction accelerated, the temperature of the universe would rise inexorably. Eventually, all matter in the universe would be compressed into an increasingly small volume. The temperature would rise to levels that would break down atomic structures. Ultimately, the entire universe would collapse back into a singularity similar to the one from which it emerged, infinitely dense, infinitely hot, containing all the matter and energy that once made up the vast cosmos. The horror of the Big Crunch lies in its claustrophobic inevitability. The walls of reality closing in from all sides, the temperature rising until all structure, all complexity, all life becomes impossible. It is cosmic death, not by ice, but by fire, the ultimate cremation of everything that ever was. However, some theoretical physicists have proposed that a Big Crunch might not be the absolute end. Perhaps as the universe collapses back to a singularity, conditions could arise for another Big Bang, another expansion, another universe emerging from the remains of our own. This concept, known as the Big Bounce, suggests a cyclical cosmos, endlessly expanding and contracting, dying and being reborn. At first glance, this might seem more comforting than the finality of the Big Freeze or the Big Rip. There is a certain poetic appeal to the idea of cosmic reincarnation, the universe itself undergoing a cycle of death and rebirth. But upon deeper reflection, the Big Bounce scenario contains its own unique horror. For even if the universe is reborn, would anything of our reality persist in the next iteration? Would the laws of physics remain the same, or would they be reset, randomized? Would there be any continuity of information, any memory of what came before? Most physicists think not. Each cycle would be, in effect, an entirely new universe, with no connection to what came before. Everything achieved in our cosmos, every civilization, every discovery, every moment of beauty or understanding would still be permanently lost, replaced by something entirely other, something that has no connection to what we were. Moreover, if the universe has always existed in such a cycle, undergoing countless bounces throughout an infinite past, this raises disturbing questions about the nature of existence itself. Are we in any way unique, or are we merely one iteration among an infinite series, doomed to be repeated with endless variations throughout an eternal cycle of cosmic rebirth? Is free will merely an illusion if everything that happens has happened innumerable times before and will happen innumerable times again? These questions border on the metaphysical, touching on concepts of determinism and eternalism that philosophers have wrestled with for centuries. Beyond these conventional end-of-universe scenarios lies an even stranger possibility, one that challenges our fundamental understanding of reality itself, the concept of Boltzmann brains. Named after the 19th century physicist Ludwig Boltzmann, this concept emerges from considering the implications of entropy in an eternal universe. Boltzmann proposed that, given enough time, random fluctuations in a high-entropy system could occasionally produce local decreases in entropy, islands of order in a sea of chaos. If the universe lasts forever, or at least an extremely long time, such fluctuations would inevitably occur. The disturbing implication is that it is statistically far more likely for a smaller ordered system to randomly emerge than a larger one. A single conscious brain, with all the memories and perceptions of a lived existence, requires far less ordered matter than an entire universe with consistent physical laws and billions of years of evolution. In other words, if our consciousness is the result of random fluctuations in entropy, it is vastly more probable that we are isolated brains that have spontaneously formed, complete with false memories of a universe that never existed, than that we are actual beings in a real, ordered cosmos with billions of years of history. This leads to a profoundly unsettling possibility. What if your entire existence, your memories, your perceptions of the world around you, the sensation of reading these words right now, is merely an illusion, a random configuration of particles that happen to form a conscious entity with false memories of a universe that never was? What if you are, in fact, a disembodied consciousness floating alone in a vast sea of entropy, experiencing a hallucinated reality that will last only moments before dissolving back into chaos? The horror of the Boltzmann brain hypothesis lies in its solipsistic implications, the suggestion that reality itself might be an illusion, a momentary decrease in entropy that creates the false impression of an ordered universe with a consistent history. It challenges our most fundamental assumptions about existence and raises disturbing questions about the reliability of our perceptions and memories. Of course, most physicists don't believe we are actually Boltzmann brains. Various arguments have been made against the hypothesis, including the observation that if such brains were constantly forming from random fluctuations, the vast majority would be in states of extreme confusion, experiencing chaotic and inconsistent realities, not the ordered, consistent universe we appear to inhabit. Nevertheless, the mere possibility serves as a reminder of how tenuous our grasp on reality might be, and how the fundamental nature of existence remains, in many ways, mysterious. Beyond these scientific speculations about the end of the universe lies an even more fundamental horror, the question of meaning in a finite cosmos. If the universe will eventually end, if all trace of everything that ever existed will one day be erased, what meaning can we ascribe to our actions, our civilizations, our very existence? This question has haunted philosophers and theologians for millennia, long before modern cosmology provided scientific models for the end of everything. In the face of inevitable cosmic extinction, what value does anything have? Does the fact that everything will eventually be forgotten render all achievement meaningless? Is a universe with an expiration date ultimately pointless? These questions touch on the deep existential angst that accompanies awareness of our own mortality, but amplified to a cosmic scale. It's not just that you will die, or that humanity will eventually go extinct, or even that life itself will someday vanish from the universe. It's that the very stage upon which the drama of existence plays out will itself disappear, leaving not even the memory that anything ever was. Some find this prospect unbearably bleak. If nothing ultimately matters because nothing ultimately endures, why strive for anything? Why create? Why love? Why seek to understand a universe that will eventually forget we ever existed? This cosmic nihilism can seem like the only rational response to the knowledge of ultimate extinction. Yet others find a strange sort of liberation in the finite nature of the cosmos. If nothing is eternal, then perhaps meaning doesn't require permanence. Perhaps value can exist in the moment, in the experience of being, in the connections we form and the understanding we achieve, even if all of it is ultimately transient. In a universe without inherent purpose or permanent record, we are free to create our own meaning, to value what we choose to value, without reference to some eternal standard. Consider too that even in a universe doomed to eventual extinction, the implications for our lived experience are minimal. The timeframes involved in most cosmic death scenarios are so vast as to be effectively meaningless on human scales. Even the most accelerated version of the Big Rip would likely not begin to affect galactic structures for billions of years, far longer than humanity has existed, and likely far longer than our species will survive in its current form. In this sense, the horror of cosmic extinction is primarily philosophical rather than practical. It raises profound questions about meaning and purpose, about the value of existence in a finite universe, but it doesn't materially impact how we experience our lives, or what we might achieve as a species or a civilization during our brief moment on the cosmic stage. And yet, the knowledge of the end remains. Like our individual awareness of our own mortality, it colors our perception of existence, infusing it with a poignancy that would be absent in an eternal cosmos. Everything becomes more precious when we know it cannot last forever. Every moment of beauty, every connection, every insight gains a certain luminosity against the backdrop of inevitable extinction. Perhaps this is why we continue to strive, to create, to seek understanding, even in the face of cosmic impermanence. We are, after all, creatures of this universe, shaped by its laws and rhythms. Our drive to persist, to grow, to understand, to connect, these are not separate from the cosmos, but expressions of it. We are the universe becoming aware of itself, if only for a brief moment between eternal silences. And in that awareness, in that brief flicker of consciousness in the vast darkness, perhaps there is meaning after all. Not a meaning imposed from outside, not a purpose that transcends the physical cosmos, but a meaning that emerges from within, from the simple, astonishing fact that matter has arranged itself, however briefly, into forms capable of contemplating their own existence and the existence of everything around them. In the end, the ultimate cosmic horror may not be that the universe will die, but that in its dying, it will take with it all record that anything ever lived, that consciousness ever arose, that beauty ever existed. The tragedy is not that we will end, but that it will be as if we never were. And yet, paradoxically, it is our awareness of this very fact, our ability to contemplate the ultimate fate of everything, to grasp the full sweep of cosmic history and our tiny place within it, that gives our existence its peculiar poignancy and worth. We are the eyes with which the universe sees itself, the mind with which it contemplates its own being and non-being. That alone, perhaps, is enough to give meaning to our brief appearance on the cosmic stage. For now, the stars still shine, galaxies still wheel through the void, light still moves across the cosmos, carrying with it the echoes of creation. And we are here to witness it, to wonder at it, to seek to understand it, even knowing that one day, in the unimaginably distant future, all of it, including the very fact that we ever existed at all, will disappear without trace. There is horror in that knowledge, yes, but there is also a strange, solemn beauty, the beauty of the transient, the ephemeral, the briefly radiant against the dark. In our contemplation of the end of everything, we touch something profound about the nature of existence itself, that it is defined as much by its ending as by its beginning, that its preciousness lies precisely in its impermanence. And so we continue, carrying within us the knowledge of ultimate extinction, yet still striving, still creating, still seeking connection and understanding. For what else can conscious beings do, in the brief moment allotted to them, but live as fully as possible in the light before the final darkness falls? The stars will eventually burn out. The universe will grow cold or collapse in fire or tear itself apart or reset in an endless cycle. And yet here and now we exist. We think, we feel, we wonder. That is our defiance against the ultimate cosmic horror. Not that we can prevent the end, but that we can make something beautiful and meaningful in the time before it comes. And perhaps that is enough. Not immortality, not eternal significance, but the simple, profound fact of having been, of having witnessed the cosmos in all its terrifying grandeur, of having been, for one brief moment in the vast sweep of time, the universe knowing itself. In the face of the ultimate cosmic horror, the end of everything, that may be the only victory available to us, but it is, in its way, enough. As we reach the end of our journey through the most terrifying aspects of the cosmos, a question inevitably arises. What is truly the scariest thing in the universe? Is it the vast emptiness of the Bootes void, stretching across hundreds of millions of light years? The crushing power of black holes that can tear apart matter, atom by atom? The inevitable heat death that awaits all existence? Or perhaps the possibility that advanced alien civilizations might view us as we view insects, with casual indifference to our survival? Each of these cosmic horrors touches on something profound about the human condition and our place in the universe. Yet perhaps the most fundamental terror, the one that underlies all others, is not any specific phenomenon, but rather the universe's profound indifference to our existence. The cosmos, in all its vast complexity and breathtaking beauty, was not made for us. It does not care about us. It does not recognize our achievements, sympathize with our suffering, or acknowledge our existence in any way. The same physical laws that allowed for the emergence of life and consciousness also create magnetars that could sterilize entire regions of space, black holes that devour everything in their path, and an ever-expanding void that will eventually render all life impossible. This indifference is something our minds struggle to accept. Throughout human history, we have created myths, religions, and philosophies that place humanity at the center of cosmic purpose. We have imagined the universe as the creation of beings who resemble us, who care about our moral choices, who have plans for our future. We have sought to inscribe meaning onto the stars themselves, seeing patterns and portents in their arrangements, imagining that their movements reflect our tiny lives. These are comforting notions. They provide a sense of cosmic significance, a feeling that our brief existences matter beyond the confines of our planet, our solar system, our galaxy. But modern astronomy and cosmology tell a different story, one in which humans are vanishingly insignificant on the scale of the universe, our entire species occupying less than an eye blink in cosmic time, our greatest civilizations less consequential to the universe than a single grain of sand is to all Earth's beaches. Consider the scale. Our entire planet is but a mote of dust compared to the Sun. The Sun itself is merely one star among hundreds of billions in the Milky Way galaxy. And the Milky Way is just one galaxy among trillions in the observable universe. If all of human civilization were suddenly wiped out by some cosmic catastrophe, the universe would continue, utterly unchanged and unaware that we had ever existed at all. This cosmic insignificance cuts against our deeply held intuition that we matter, that our lives have meaning beyond what we ourselves create. And yet, paradoxically, it is our ability to comprehend this very insignificance that makes humanity remarkable. We are, as far as we know, the only entities in our corner of the cosmos capable of understanding the universe's vastness and our tiny place within it. We alone can contemplate the birth of stars, the death of galaxies, the eventual fate of everything. We alone can look up at the night sky and feel simultaneously dwarfed by its immensity and connected to it at the most fundamental level, knowing that the elements in our bodies were forged in stellar furnaces billions of years ago. In this awareness lies both the deepest cosmic horror and a strange sort of dignity. We are the universe become conscious of itself, matter arranged in such a way that it can contemplate its own existence. That this arrangement is temporary, that consciousness appears to be a brief phenomenon in cosmic history, doomed to eventually flicker out as the universe continues its inexorable evolution, only makes it more precious, more worthy of protection and celebration. The terror of cosmic insignificance has haunted human thought for centuries, finding expression in various philosophical traditions. Existentialist philosophers like Albert Camus and Jean-Paul Sartre grappled with the apparent absurdity of seeking meaning in an indifferent universe. P. Lovecraft built entire mythologies around the psychological impact of confronting cosmic scales and alien mindsets, utterly unconcerned with human well-being. Even religious traditions have struggled with the question of why a deity who supposedly cares about humanity would create such an unimaginably vast cosmos in which we occupy such a minuscule place. These philosophical and artistic responses to cosmic insignificance reveal something important about the nature of horror itself. It often stems from the violation of our expectations, the shattering of our assumptions about how reality works and our place within it. We expect to matter. We expect the universe to in some way acknowledge our existence, to operate according to principles that make sense to us. When we discover that reality is vastly larger, more complex, and more indifferent than we imagined, the resulting cognitive dissonance manifests as a form of existential dread. This dread is amplified by our understanding of cosmic timescales. The universe has existed for approximately 13.8 billion years before humans evolved, and it will continue to exist for trillions of years after our species is gone. The entire span of human civilization, from the first agricultural settlements to our current technological society, represents less than 1/10,000th of 1% of cosmic history thus far. And the future stretches out vastly longer than the past. When we contemplate these timescales, our lives, which seem so significant to us, shrink to practical nothingness. The most famous historical figures, the most influential artists, the most brilliant scientists, all will eventually be forgotten as thoroughly as if they had never existed at all. Not just forgotten by other conscious beings, who will themselves eventually disappear, but forgotten by the universe itself, every trace of their existence erased by the relentless erosion of entropy. And yet, despite this bleak assessment, something remarkable happens when we fully confront the horror of cosmic insignificance. We discover a kind of freedom. If the universe assigns no inherent meaning to our lives, then we are free to create our own meaning. If no cosmic plan requires our participation, then we can chart our own course. If no universal moral law is inscribed in the fabric of reality, then ethics becomes a human creation, something we develop together, based on our shared needs and values, rather than something imposed from outside. This is the paradoxical gift of cosmic horror. In showing us our insignificance, it also shows us our autonomy. We're not cosmic protagonists, but neither are we merely fulfilling predetermined roles in some grand universal drama. We are, instead, temporary arrangements of matter and energy that have somehow developed the capacity for self-reflection, for choice, for meaning-making. That this capacity emerged in an indifferent universe makes it no less remarkable. Indeed, perhaps it makes it more so. The horror of the cosmic void thus gives way to a kind of existential courage, the willingness to create meaning in the face of meaninglessness, to forge connections in a fundamentally disconnected cosmos, to value consciousness despite its temporary nature, to cherish life despite its cosmic insignificance. This courage is not about denying the horror, but about embracing it as the necessary backdrop against which all human meaning must be constructed. Consider how differently we might view our petty conflicts, our tribal divisions, our national boundaries if we truly internalize the cosmic perspective. If we understood that we are all equally insignificant against the vastness of space and time, all equally temporary, all equally precious in our brief moments of awareness. The cosmic horror of insignificance thus contains the potential for a profound human solidarity. Perhaps this is why astronomy, despite revealing many of the terrifying aspects of the universe we've explored, remains one of the most popular sciences among the general public. In showing us our cosmic insignificance, it paradoxically connects us to something larger than ourselves. In revealing the indifference of the universe, it highlights the preciousness of the connections we form with one another. In demonstrating the vastness of space and time, it emphasizes the unique value of the here and now. The cosmic horrors we've examined throughout this journey, from deadly stellar phenomena to the ultimate fate of everything, are not merely frightening curiosities. They are windows into the true nature of reality, reminders that the universe is far stranger, far more complex, and far more indifferent than our evolved intuitions would lead us to believe. And in this recognition lies both existential dread and existential opportunity. For if the universe does not care about us, then it falls to us to care about one another. If cosmic time will eventually erase all trace of our existence, then it falls to us to make our brief moment meaningful through our connections, our creations, our compassion. If the cosmos is characterized by emptiness and isolation, then it falls to us to create islands of meaning and community within it. This perhaps is the most powerful response to cosmic horror, not denial, not despair, but a clear-eyed acceptance coupled with a determination to create meaning despite the void, to recognize our insignificance without allowing it to diminish the value we place on consciousness, on life, on the brief miracle of awareness. The ancient philosophers had a concept known as amor fati, love of fate, which referred to an attitude of embracing all aspects of life, including suffering and loss, as necessary components of a complete existence. Perhaps what we need in the face of cosmic horror is something we might call amor universi, love of the universe, an attitude that embraces even the terrifying aspects of reality as part of what makes existence what it is. This does not mean denying the horror. The universe contains phenomena that can and would destroy us without the slightest hesitation or remorse. From gamma-ray bursts that could sterilize entire regions of the galaxy, to vacuum decay that could rewrite the laws of physics themselves, to the simple, relentless increase of entropy that will eventually render all life impossible. These are genuine existential threats that cannot be wished away. But alongside these horrors exist wonders of equal magnitude. The birth of stars from vast molecular clouds, the dance of galaxies through the cosmos, the emergence of life from non-living matter, the evolution of consciousness from simple biological processes, the development of science, art, philosophy, and all the other fruits of human creativity. The universe that does not care about us is the same universe that produced us, that made possible everything we value. And perhaps most wondrous of all is the simple fact that we can comprehend any of this. That arrangements of matter as insignificant as ourselves can nevertheless understand something of the nature of reality, can trace cosmic history back to its origins, can predict the behavior of phenomena millions of light years away, or forecast the fate of the universe trillions of years in the future. This capacity for understanding does not make us cosmically significant, but it does make us significant to ourselves, and that perhaps is enough. In the end, the true horror of the universe may be inseparable from its true wonder. The same vastness that dwarfs us also inspires us. The same indifference that threatens us also frees us. The same laws that will eventually bring about the end of everything also made possible the emergence of life and consciousness in the first place. Horror and wonder are not opposites but complementary aspects of a full engagement with reality. As we conclude our journey through the most frightening aspects of the cosmos, it's worth remembering that we experience these horrors not directly, but through the medium of human understanding. The universe does not present itself to us as either terrifying or beautiful. It simply is. The horror, like the beauty, exists in the relationship between reality and consciousness, in the meanings we construct as we try to comprehend the incomprehensible. And in this construction of meaning, this ongoing attempt to understand reality in all its terrifying grandeur, we engage in an activity that is uniquely human and uniquely valuable. We transform mere existence into experience, mere facts into understanding. We create islands of meaning in a sea of cosmic indifference. Is this enough to counterbalance the horror? That is a question each consciousness must answer for itself. But perhaps it is not about counterbalancing at all. Perhaps it is about embracing the totality of what is, the horror alongside the wonder, the insignificance alongside the meaning, the eventual extinction alongside the present moment of awareness. For we are part of this universe, not separate from it. The same processes that created magnetars and black holes that will eventually bring about the heat death of everything also created us. We are not observers of cosmic horror, but expressions of the same reality that produces it. And in that recognition lies a kind of cosmic belonging, a strange sort of homecoming. Look up at the night sky, feel the terror of its vastness, its emptiness, its indifference. Feel the wonder of its beauty, its complexity, its profound connection to your own existence. Feel the horror and the wonder together, not as contradictions, but as complementary aspects of a single reality. This perhaps is what it means to truly understand our place in the cosmos. Not to deny the darkness, but to see it alongside the light. Not to escape insignificance, but to create meaning despite it. The universe doesn't care whether you exist. It does not notice your achievements or your failures, your joy or your suffering. It will continue long after all trace of humanity has vanished from existence. These are terrifying truths, and they cannot be avoided or denied. But you are here now, aware, capable of understanding something of the nature of reality, capable of creating meaning, capable of connection. And that, not cosmic significance, not eternal importance, But the simple, profound fact of conscious existence is the gift that counterbalances the horror. Not because it makes the horror less real, but because it makes the brief moment of awareness more precious. We began this journey by asking what makes the universe so terrifying. We end it by recognizing that the same qualities that terrify us, vastness, complexity, indifference, also make possible everything we value. The horror exists, it is real, but it is not the only reality. Alongside it exists the equally real wonder of consciousness, of understanding, of connection. In the face of cosmic horror, this is our response. Not denial, not despair, but a clear-eyed acceptance coupled with a determination to make our brief moment meaningful, to see the darkness and acknowledge it without being consumed by it, to recognize our cosmic insignificance without allowing it to diminish the value we place on our temporary awareness. For we are the universe become conscious of itself, matter arranged in such a way that it can contemplate its own existence. That this arrangement is temporary, that consciousness appears to be a brief phenomenon in cosmic history, doomed to eventually flicker out as the universe continues its inexorable evolution, only makes it more precious, more worthy of protection and celebration. The horror exists, but so do we, for now, in this moment, aware and alive in a cosmos that neither knows nor cares that we are here. And in that awareness, in that aliveness, we find both our response to the horror and our reason for continuing despite it. Not because we matter to the universe, but because we matter to each other and to ourselves. Look up at the stars, feel the horror and the wonder together. This is what it means to be human, to know our place and to create meaning anyway, to see the darkness and to kindle lights against it, however temporary, however small. For we are brief candles in an infinite night, but while we burn, we illuminate our small corner of the cosmos with something that, even if it lacks cosmic significance, nevertheless matters deeply to us: consciousness, connection, compassion. And perhaps that is enough.